For 70 years, our understanding has been fundamentally flawed. The Milky Way galaxy, our cosmic home, has been underestimated in size. It is not 100,000 light-years across as commonly believed, but rather double that span, perhaps even exceeding it. We have, for generations, been operating within a galactic structure twice the scale previously taught, depicted in every classroom, chronicled in every academic journal, and ingrained in our collective astronomical knowledge. The advent of cutting-edge technology has finally unveiled this truth, a revelation that profoundly alters our perspective. It impacts how we gauge the immensity of the cosmos, the eventual fate of our encounter with the Andromeda Galaxy, and the very question of whether we are alone in the universe. If you are intrigued to witness how scientific understanding has been revolutionized regarding the dimensions of our galactic abode, please consider liking this video and subscribing. This is the narrative of the most significant recalibration in modern astrophysics. Prepare yourselves, our journey begins. Open your preferred astronomy reference. Locate the depiction of the Milky Way galaxy, that graceful spiral, complete with precise measurements indicating 100,000 light-years in diameter. That depiction is incorrect. Utterly and demonstrably incorrect. Not merely slightly inaccurate or outdated by a minor margin, but wrong by a factor of 2. Every classroom poster, every animated documentary, every diagram presented on platforms like Wikipedia that you have relied upon, all portray a galaxy at merely half its actual magnitude. For years, the scientific community has harbored suspicions that something was amiss. However, the evidence emerged piecemeal. Subtle hints, perplexing anomalies that resisted integration into existing models. We observe stars at the galaxy's periphery moving at velocities far exceeding expectations, satellite galaxies executing orbits at improbable distances, and mass calculations that consistently failed to reconcile. Subsequently, definitive measurements began to proliferate, fueled by data from the Gaia spacecraft, observations from the James Webb Space Telescope, and extensive radio telescope surveys meticulously mapping hydrogen clouds at the galaxy's outermost reaches. Each new instrument consistently revealed the identical, astonishing pattern. The Milky Way extends far beyond the boundaries we had previously defined. The challenge was not due to any lack of diligence on the part of astronomers. Rather, it stemmed from the inherent difficulty of measuring our own galaxy from within its confines. Envision attempting to delineate the perimeter of New York City while standing precisely at its epicenter. The edges are obscured, and stepping outside for a comprehensive vantage point is impossible. You are enveloped by the city's structures, its brilliant illumination, and its ceaseless din. Such is our predicament, situated on one of its spiral arms, 26,000 light-years from the core, immersed in a sea of stars and interstellar dust. For decades, scientists employed a rudimentary methodology. They focused on the most luminous stars discernible in every direction. Where the stellar density began to diminish, they drew a conceptual line, designating it as the galaxy's boundary. This yielded the 100,000 light-year figure. The matter was considered settled. However, the reality was never that straightforward. A galaxy does not possess a sharp, definitive edge, akin to a dinner plate. Instead, its stellar population gradually fades. Stars disperse outwards in ethereal streams and diffuse clouds. Furthermore, dark matter, an enigmatic and substantial component, extends considerably further. The earlier measurements only accounted for the readily observable, the prominent features. They overlooked the vast, encompassing halo of material that envelopes the entire structure. This is what revolutionized our understanding. Scientists began to meticulously track stellar streams, vast cosmic rivers composed of stars, ripped from smaller galaxies that the Milky Way incorporated into itself eons ago. These streams traverse space like spectral remnants of ancient galactic interactions, and their trajectories provide invaluable insight into the galaxy's true gravitational dominion. Upon charting these streams, researchers discovered them extending far beyond our previously assumed galactic perimeter, reaching distances of 200,000 light-years, and potentially even greater. The Milky Way is a colossal entity, and for too long, we have been measuring merely its shadow. This groundbreaking discovery does more than simply alter numerical values in academic texts. It fundamentally reshapes our comprehension of galactic architecture. It modifies the projected timeline for the Andromeda Galaxy's inevitable collision with our own and doubles the volume of space we must scrutinize for potential extraterrestrial life. Every calculation predicated on the previous size estimate now requires complete revision. However, perhaps the most unsettling implication is this: if we have so profoundly misjudged the dimensions of our own galaxy, what other astronomical assumptions might be equally erroneous? How many other galaxies are, in fact, twice as expansive as our current models suggest? Imagine being blindfolded and placed in the heart of the Sahara Desert, tasked with the responsibility of measuring its entire expanse. You are forbidden from removing the blindfold and cannot utilize GPS technology. Your only sensory inputs are the feel of sand beneath your feet and the sound of the wind. How accurately could you possibly map its boundaries? This analogy aptly captures the challenge faced by astronomers attempting to ascertain the true scale of the Milky Way. We reside on a planet that orbits an unremarkable star, situated on an outer spiral arm. Dense clouds of interstellar dust obscure our view in virtually every direction. The galactic core is concealed behind formidable barriers of gas and debris. Through optical telescopes, we perceive perhaps only 10% of our galaxy's totality. The remainder remains hidden, veiled within infrared and radio wavelengths, and shrouded in darkness. In stark contrast, measuring the Andromeda Galaxy is a relatively straightforward endeavor. It is situated 2.5 million light-years distant, allowing us to perceive its entirety simultaneously, from edge to edge, and from top to bottom. We can capture its image, map its spiral arms, and enumerate its star clusters with relative ease. Attempting to chart our own galaxy is akin to trying to photograph one's own face without the aid of a reflective surface, while simultaneously navigating through an impenetrable fog. In the early days of astronomical inquiry, pioneers had no alternative but to measure what they could perceive. They diligently tracked Cepheid variable stars, whose luminous pulsations occur at predictable intervals, and calculated the distances to globular clusters, ancient congregations of stars that encircle the galactic center. Their efforts were akin to assembling a complex puzzle while blindfolded, constructing a map piece by painstaking piece. The pivotal breakthrough occurred when scientists recognized the potential of utilizing motion as a proxy for light. Every celestial body within the galaxy adheres to a gravitational orbit around its center, stars, nebulae, and entire star clusters alike. Their velocities are dictated by the collective mass exerting gravitational influence. By measuring these velocities, astronomers could subsequently deduce the mass, and from that, estimate the galaxy's overall dimensions. However, a perplexing discrepancy soon emerged. The velocities observed at the galaxy's periphery were unexpectedly high. Based on the visible mass alone, these stars should have been flung outwards into the void of space. Something unseen, something possessing significant mass, was evidently retaining them in their orbits. This invisible entity was identified as dark matter, comprising an immense halo that enshrouds the galaxy like a protective gravitational cocoon. This is precisely where the earlier measurements faltered. They exclusively accounted for tangible, observable matter, luminous stars, incandescent gas clouds, and brilliant nebulae. They neglected the indispensable invisible mass, the dark scaffolding that underpins the entire galactic structure. This oversight constituted the fundamental error. Modern telescopic advancements have profoundly altered this landscape. The Gaia spacecraft meticulously tracks the precise trajectories of over 1 billion stars. Radio telescopes are employed to map the distribution of hydrogen gas that extends into the galaxy's outer halo. Infrared instruments possess the capability to penetrate the dust clouds that obstruct visible light. Each technological innovation illuminates a distinct stratum of the galaxy. Furthermore, researchers began leveraging satellite galaxies as crucial reference points. Our Milky Way is orbited by dozens of smaller galactic companions. Prominent among these are the Large Magellanic Cloud and the Small Magellanic Cloud, along with numerous dwarf galaxies such as the Sagittarius Dwarf. These satellite galaxies maintain their orbits based on the combined gravitational pull of our galaxy, encompassing both its visible and invisible components. By meticulously charting their orbital paths, astronomers are effectively mapping the galaxy's true gravitational field. Upon synthesizing all this accumulated data, the results presented a startling revelation. The Milky Way is not the moderately sized spiral galaxy we had envisioned. Instead, it is a formidable entity, a true galactic titan, with a diameter twice as great and a mass potentially triple that of previous estimates. If discerning our own galaxy's extent from within proves so challenging, consider the implications for measuring distances beyond its confines. Stellar streams, while sounding esoteric, are essentially cosmic crime scenes, immutable records of galactic violence frozen in time. Millennia ago, smaller galaxies ventured too close to the Milky Way's gravitational embrace. Our galaxy's immense pull then captured them, tearing them asunder and stretching their stellar contents like molten taffy. These stars did not simply vanish. They were dispersed into elongated rivers of light, forming vast streams that encircle our galaxy. Some of these streams possess a breadth that surpasses Earth's entire orbital path around the Sun. Others contain thousands of stars moving in perfect celestial synchronization. Previously, these streams were largely overlooked, dismissed as mere background noise, faint, distant, and seemingly inconsequential. However, they are now recognized as our most reliable cosmic rulers for determining the galaxy's true dimensions. The significance of these streams lies in their adherence to gravitational principles. Every star within a stream follows an orbital path dictated by the galaxy's total mass. By analyzing the trajectory of a stellar stream, one can effectively ascertain the strength of the gravitational field. This method eliminates guesswork and assumptions, relying purely on the laws of physics. The Sagittarius stream, a particularly well-documented example, encircles the entire Milky Way multiple times, resembling a ribbon draped around a gift. Astronomers who trace this stream across the celestial sphere determine that it extends far beyond the previously recognized galactic perimeter. The stream continues onward, signifying that the Milky Way's gravitational influence also extends progressively further. Next, consider the GD1 stream, a delicate river of stars located in the galaxy's outer halo. Researchers meticulously mapped its curvature and uncovered an anomaly that defied conventional understanding. The stream exhibited a bending pattern that necessitated a far greater mass than could be accounted for by the visible components of the galaxy. This led to a critical conclusion: either our understanding of physics was fundamentally flawed, or a substantial, unseen component was at play. That unseen component, as is increasingly evident, is dark matter. These stellar streams, much like invisible ink revealed under ultraviolet light, illuminated the presence and influence of dark matter. The gravitational forces shaping these celestial rivers emanate from matter that remains imperceptible to direct observation, matter that extends twice as far as the visible stars. Yet, the implications extend even further into the realm of the astonishing. Scientists have identified streams orbiting at distances previously presumed to be intergalactic space, vast, empty voids between galaxies. However, these regions are proving not to be empty at all. These streams unequivocally demonstrate that the Milky Way's gravitational reach extends far beyond what anyone had previously conceived. Our galaxy does not simply cease at its visible edge. It continues to exert its influence, to claim territory, and to maintain dominion. The orphan stream, in particular, evokes a sense of profound cosmic mystery. It orbits at such an extreme distance that for many years, astronomers debated whether it was genuinely part of the Milky Way or belonged to another galactic entity entirely. Subsequent, more precise measurements have definitively confirmed its origin. This stream is indeed ours, unequivocally placing the Milky Way's boundary at least that far outward. Each newly discovered stream has contributed additional thousands of light-years to the galactic radius, 5,000 light-years here, 10,000 there. The cumulative figure steadily climbed, 120,000 light-years, 150,000, 180,000. Stellar streams have provided astronomers with an invaluable asset, empirical validation. While the precise location of the visible disk's edge might be subject to debate, and the transition from galactic darkness to intergalactic space may remain a point of discussion, there is no room for argument when it comes to a stream of stars meticulously orbiting in unison. Their trajectories represent an indisputable truth. And this truth has consistently pushed the galactic boundary outward, further than was comfortable, further than could be explained by established models. 200,000 light-years. The stream's path attested to it. The mathematical calculations confirmed it. The observational data corroborated it. The question is no longer how vast the Milky Way truly is. The pertinent question now is how we could have overlooked such a monumental reality for so long. What you are currently perceiving as the Milky Way is, in essence, its skeletal structure, the luminous framework, the readily apparent components. Fully 90% of the galaxy remains imperceptible. Dark matter is no longer a theoretical construct. It is a scientifically validated, measured, and mapped entity. While direct visual detection is impossible, its pervasive effects are observable across the cosmos. Stars orbit at velocities that defy expectations based on visible mass alone. Galaxies maintain their structural integrity, resisting the centrifugal forces that would otherwise cause them to disperse. Light from distant celestial objects undergoes gravitational bending as it traverses the invisible mass. The accumulated evidence is overwhelmingly conclusive. Within the Milky Way, dark matter does not merely contribute to its overall mass. It fundamentally shapes its very architecture. Visualize a skyscraper where you can only see the windows, yet remain oblivious to the intricate steel framework supporting them. Such is the nature of our galaxy. The stars serve as the windows, while dark matter constitutes the indispensable framework. Scientists estimate that dark matter's mass exceeds that of visible matter by a ratio of 10 to 1. For every star you can observe, there exists 10 times that amount of invisible mass in its vicinity. This enigmatic material forms a colossal halo that envelopes the galaxy, a spherical, diffuse expanse that extends far beyond the boundaries of the visible disk. The older estimations deliberately disregarded this halo, focusing exclusively on the prominent spiral arms, the radiant core, and other readily apparent features. Consequently, the galaxy was perceived as being 100,000 light-years in diameter, merely reflecting the point where the visible stars diminished in density. However, dark matter persists much further, extending outward to twice that distance, and potentially even more. Consider it analogous to an iceberg. The visible portion above the water represents the observable galaxy. Submerged beneath the surface, concealed from view, lies a colossal mass of ice, 10 times the size of its visible counterpart. This submerged mass is the dark matter halo. The true dimensions of the galaxy encompass both components. Researchers meticulously map this halo through the phenomenon of gravitational lensing. When light originating from a distant galaxy traverses the vicinity of the Milky Way, it is subtly deflected by the galaxy's dark matter. By measuring the degree of this deflection, scientists can accurately calculate the associated mass. The results obtained from these measurements have proven profoundly surprising. Our galaxy's dark matter halo extends outwards to an astonishing distance of nearly 400,000 light-years, when accounting for the faint outer regions. However, a perplexing nuance arises. Astronomers engage in ongoing debate regarding the precise demarcation point. When does the Milky Way definitively conclude and intergalactic space commence? Is the boundary defined by a halving of dark matter density, or perhaps a quarter, or even a tenth? There is no universally agreed upon demarcation. Instead, there is a gradual, imperceptible dissipation into the void. For practical purposes, astrophysicists utilize a metric known as the virial radius. This signifies the boundary within which matter remains gravitationally bound to the galaxy. All objects within this radius collectively orbit the galactic center. Beyond this radius, space is considered truly empty. For the Milky Way, this virial radius is estimated to lie between 200,000 and 250,000 light-years, effectively doubling the earlier estimations. All of this is attributable to the pervasive influence of invisible mass. This revelation fundamentally alters our perception of galactic structure. Galaxies are not merely isolated islands of stars adrift in the vacuum of space. Instead, they are colossal halos of dark matter, with stars dispersed throughout their central regions. The visible component can be considered ornamental, while the invisible component represents the substance. And if our own galaxy harbors such a significant amount of hidden mass, it is logical to assume that every other galaxy does as well. The universe, it appears, has become considerably more massive. The Milky Way is not an isolated entity. Dozens of smaller galaxies orbit our own, akin to moons revolving around a planet. These are referred to as satellite galaxies, and their existence has significantly recalibrated our cosmic address. The Large Magellanic Cloud, a conspicuous object visible from the southern hemisphere as a hazy celestial smudge, contains an estimated 30 billion stars. The Small Magellanic Cloud resides in close proximity, harboring an additional 7 billion stars. Beyond these, we find numerous dwarf galaxies, including the Sagittarius Dwarf, Draco Dwarf, and Ursa Minor Dwarf. Each of these is a miniature galaxy in its own right, possessing its own unique collection of stars, its own distinct history, and its own orbital path. For an extended period, scientists regarded these satellite galaxies as mere neighbors, independent entities traversing the cosmic expanse. However, recent measurements have illuminated a different reality. They are not merely passing by. They are gravitationally bound to us, ensnared within the Milky Way's sphere of influence. This realization has precipitated a paradigm shift in our understanding. By precisely measuring the orbital velocity of a satellite galaxy, one can accurately calculate the mass responsible for its gravitational tether. A greater mass results in tighter orbits, while a lesser mass allows objects to drift away. The satellite galaxies, in their specific orbital distances and speeds, provide undeniable evidence of our galaxy's total gravitational pull. The Large Magellanic Cloud, situated approximately 160,000 light-years away, completes an orbit around the Milky Way roughly every 1.5 billion years. For it to maintain such an orbit at that specific distance, our galaxy must possess a mass considerably greater than previously estimated. Researchers have meticulously analyzed the orbits of dozens of these satellite galaxies and consistently observed the same pattern. They all orbit at greater distances than anticipated, and they move at velocities exceeding predictions. The sole plausible explanation for this phenomenon is that the Milky Way is, in fact, significantly larger and more massive than we had previously comprehended. However, the most significant breakthrough arose from the study of tidal streams. When a satellite galaxy ventures too close to the Milky Way, its gravitational forces begin to tear it apart. stars are progressively pulled away, forming elongated trails. The Sagittarius dwarf galaxy is currently undergoing this process of disintegration. Its stars stretched across the sky in a stream that encircles the entire galaxy. These tidal tails function as invaluable test masses, indicating regions of maximum gravitational intensity, areas where the gravitational field weakens, and ultimately delineating the galactic boundary. By mapping a sufficient number of these tidal streams, astronomers can effectively chart the extent of the galaxy. The discoveries made through this analysis have been nothing short of astonishing. The streams extend far beyond the previously presumed galactic perimeter, with some reaching distances exceeding 150,000 light-years, and others extending to 200,000 light-years. A few nascent indicators even suggest the presence of galactic material at even greater distances. The satellite galaxies are, in essence, vociferously proclaiming the truth. The Milky Way is an immense structure. This revelation has immediate and far-reaching implications. If our galaxy possesses such colossal dimensions, then the local group of galaxies, our immediate cosmic neighborhood, requires a fundamental reevaluation. The expanse of space separating us from the Andromeda galaxy is considerably smaller than previously calculated. The gravitational influence of each galaxy extends further, leading to earlier and more impactful interactions. Collisions are destined to occur sooner, and the process of galactic merging will commence earlier in cosmic history. Each satellite galaxy has become an indispensable data point, and every observed orbit serves as a critical measurement tool. Collectively, these observations paint a compelling portrait of a galactic leviathan, a stark contrast to the moderately sized spiral we had long envisioned. And here lies a particularly poignant aspect. Some satellite galaxies orbit at such extreme distances that their discovery is ongoing. Approximately every few years, astronomers unearth yet another dwarf galaxy concealed within observational data. Each new discovery further extends our galactic boundary by a marginal yet significant amount. The question inevitably arises, how many more such entities remain undiscovered? And precisely how much larger does the Milky Way ultimately prove to be? 200,000 light-years. This figure is so immense that its abstract meaning begins to elude comprehension. The human mind struggles to process it, to visualize it, or to truly grasp its scale. Allow me to attempt to make it more tangible. Light travels at a speed of approximately 186,000 miles per second. In the span of 1 year, light traverses roughly 6 trillion miles. Multiply that figure by 200,000. The Milky Way galaxy is, therefore, approximately 1.2 quintillion miles in diameter. Even this quantification remains abstract. Permit me to offer another perspective. If one were capable of traveling at the speed of light, the absolute velocity limit of the universe, it would still require 200,000 years to traverse the entirety of the galaxy, from one edge to the other. This timeframe represents the journey of light originating from one side of the galaxy until it finally reaches the opposite edge. Throughout this immense duration, humanity has undergone its entire evolutionary journey, progressing from primitive hunter-gatherer societies to advanced spacefaring civilizations, experiencing periods of collapse and rebirth multiple times over. To frame it differently, if our Earth were reduced to the size of a single grain of sand, the Milky Way would extend further than the distance between Earth and Saturn. In fact, it would extend far, far beyond that. Alternatively, consider this. The light you perceive emanating from the farthest reaches of the galaxy originated its journey before the advent of modern humans, before the existence of Neanderthals, and even before Homo erectus. That light has been in transit since our earliest ancestors were dwelling in arboreal environments. This sheer scale defies human intuition. Our brains have evolved to comprehend terrestrial distances we can traverse on foot, perhaps spanning hundreds of miles. Our neural architecture simply lacks the capacity to conceptualize quantities numbering in the quintillions. However, the implications of this immense scale are not purely academic. They possess direct and personal relevance to you, here and now. Doubling the galaxy's diameter effectively doubles the volume of space it encompasses. Volume scales with the cube of the radius. Therefore, if the galaxy is twice as wide, its total volume is 8 times greater. This translates to 8 times more space, 8 times more stars, and consequently, 8 times more planets. The prior estimation suggested approximately 200 billion stars within our galaxy. The revised estimate places this figure closer to 400 billion, and potentially even higher. Each of these stars could potentially host planets, and each planet could possess moons. Furthermore, many of these moons could harbor subsurface oceans. The number of potential abodes for life has, therefore, effectively doubled. Consider the profound implications of this reality. If the prevalence of life is exceedingly rare, occurring in perhaps 1 in a billion star systems, we have just significantly increased the odds by introducing 200 billion additional opportunities. If intelligent extraterrestrial life exists somewhere in the cosmos, we have effectively doubled the probability of discovering them, or of them discovering us. Moreover, this expanded galactic scale also fundamentally alters our projected timeline for cosmic events. The Andromeda Galaxy is currently hurtling towards us at a velocity of approximately 70 miles per second. When galaxies collide, their interactions are not akin to vehicular crashes. Instead, they undergo a process of merging. Stars often pass between one another, with very few actually colliding. However, the resulting gravitational upheaval profoundly reshapes the entire galactic structure. Scientists had previously calculated that the collision with Andromeda would commence in approximately 4.5 billion years. A larger Milky Way, with its extended gravitational reach, implies that the two galaxies will begin to exert gravitational influence on each other sooner. This interaction could potentially begin as early as 4 billion years from now, or possibly even less. Your descendants, should humanity endure for such an extended period, will witness a dramatic transformation of the night sky. Andromeda will appear progressively larger and brighter, eventually dominating half of the visible heavens. Subsequently, the galaxies will engage in a celestial dance, their spiral arms intertwining before ultimately coalescing into a single, massive elliptical galaxy. The figure of 200,000 light-years is not merely a number. It represents our collective future. It encompasses our past, serving as the vast stage upon which every human narrative ever conceived has unfolded within its minuscule corner. And we have only just begun to realize that this stage is, in fact, twice as expansive as we had previously believed. Andromeda is approaching. This is not a speculative hypothesis. It is a scientifically validated fact. Our neighboring galaxy is accelerating towards us at a velocity of 70 miles per second. The inevitable collision is certain. For decades, astronomers calculated that this cosmic impact would occur in approximately 4.5 billion years. Mark those calendars. However, those calculations were predicated on the assumption of the previously accepted galactic dimensions, a smaller Milky Way, with a consequently reduced gravitational reach, implying a greater spatial separation between our galaxy and Andromeda. A larger Milky Way fundamentally alters this timeline. Its gravitational influence extends further, compelling the galaxies to begin interacting sooner than anticipated. Their immense dark matter halos, stretching hundreds of thousands of light-years outward, will likely interact first. When these halos make contact, the collision process will effectively commence. Consider two individuals walking towards each other. If both are larger than initially perceived, they will inevitably encounter each other sooner. The same principle applies on a galactic scale. Current models suggest that this interaction could begin in under 4 billion years, perhaps as early as 3.5 billion years. The precise timeline remains subject to refinement as we continue to collect more accurate measurements, but the overarching trend is unequivocal. Larger galaxies invariably lead to earlier points of contact. Here is a breakdown of the sequence of events during a galactic collision. Initially, the outer halos of dark matter begin to merge, with the invisible mass of each galaxy interpenetrating the other. This phase, though imperceptible visually, is gravitationally intense. Stars within each galaxy will experience the gravitational pull from both galactic centers, leading to destabilization of their orbits. Some stellar bodies are violently ejected into the vast expanse between galaxies. Others spiral inwards towards the central mass. Then, the visible celestial disks intersect. It's not a violent collision, more like two nebulae drifting through one another. Stars are so incredibly distant from each other that direct impacts are exceedingly rare. You could comfortably house millions of Earths between neighboring stars. However, the gravitational turmoil is very real. Star creation ignites. Gaseous clouds compress. New stars burst into existence across both galactic structures. The Milky Way and Andromeda will engage in mutual orbital dances, spiraling around each other countless times. Each pass will inexorably strip away more matter. Gravitational forces will tear apart the spiral arms. Stellar debris will scatter in every conceivable direction. The once graceful formations will become contorted, disfigured, and unrecognizable. Eventually, perhaps 1 billion years following their initial encounter, the galaxies will fully coalesce. The outcome will be a colossal elliptical galaxy. No more graceful spiral arms, no more ordered disk, just a vast conglomeration of 4 trillion stars revolving in unpredictable trajectories. Astrophysicists have already christened this future galactic entity Melameda, a charming appellation for the demise of two ancient spiral systems. But the crucial question remains, will Earth endure? Will our sun survive? Will humanity still exist to witness it? Let's begin with the positive outlook. The sun will most likely withstand the merger. It resides sufficiently far from the galactic nucleus to likely evade the most ferocious zones. Earth might be propelled into a new orbital path, ejected entirely into intergalactic space, or maintain its current orbital position. The probabilities favor survival. The unfortunate news is that the sun will have long since extinguished by then. Our star possesses approximately 5 billion years of observable fuel remaining. The Andromeda encounter is slated to occur just before the sun's demise. But barely, we might have a front-row perspective on the initial phases. An expanded Milky Way has accelerated that timeline. The grand spectacle commences sooner. And here's the aspect that tends to be overlooked. What if Andromeda is also more substantial than our measurements indicate? Their estimations could be erroneous as well. If both galaxies are larger, the collision will transpire even earlier. The gravitational disarray will intensify. The ultimate merged galaxy will become even more immense. We are already observing the nascent indications. Andromeda's outer halo is extending towards us. Our halo is reaching out to theirs. The halos might already be in contact. The cosmic convergence might have subtly, imperceptibly commenced within the dark matter enshrouding both galaxies. For billion years sounds like an eternity, but in the grand timescale of the cosmos, it is merely the morrow. And the morrow has just drawn a little closer. Massachusetts. Everything ultimately hinges on mass. The Milky Way has just increased its heft. A considerable amount of heft. Trillions upon trillions of solar masses have materialized in the data. The prior estimate suggested our galaxy contained approximately 1.5 trillion times the Sun's mass. The majority of that was attributed to dark matter. The new measurements indicate 4 trillion solar masses, perhaps even more. We have tripled the estimated mass in under a decade. Here's what a solar mass signifies. Our Sun weighs approximately 2 quintillion kilograms. a figure so immense it borders on the abstract. 1 solar mass. For comparative purposes, Earth weighs 300,000 times less than that. Jupiter weighs 1,000 times less. All celestial bodies within our solar system, excluding the Sun itself, cumulatively constitute barely 1% of a single solar mass. Now multiply the Sun's mass by 4 trillion. That is the magnitude of the Milky Way, a gravitational colossus. Where did all this additional mass originate? Did the galaxy suddenly gain weight? Did matter spontaneously manifest from nothingness? Obviously not. It was always present. We simply lacked the precision to measure it accurately. The bulk of the excess mass consists of dark matter, imperceptible, undetectable, except through its gravitational influence. The earlier measurements concentrated on visible stars and gas. They extrapolated dark matter indirectly by analyzing galactic rotation curves. Stars orbit the galactic center at velocities dictated by mass. Measure the velocities, calculate the mass. However, those measurements only sampled the inner galaxy, the region populated by abundant stars where observations are straightforward. No one had precisely quantified the outer halo, where dark matter holds sway. That was the oversight. Novel methodologies have revolutionized our understanding. The orbital paths of satellite galaxies have yielded direct mass estimations at vast distances. Stellar streams have meticulously mapped the gravitational field in the peripheral regions. Computational simulations have compared our galaxy to thousands of virtual galaxies with known masses. All methodologies have converged on a consistent result: 4 trillion solar masses. The Milky Way is a heavyweight contender. This has profound implications. Greater mass translates to amplified gravitational pull. Stronger gravity signifies our capacity to retain more satellite galaxies in orbit. We can more readily dislodge stars from passing galactic neighbors. We exert a more comprehensive dominance over our local galactic neighborhood. Andromeda was consistently regarded as the senior partner, the Alpha Galaxy. However, recent assessments suggest we might be equals, or perhaps even surpass it in mass. The Milky Way and Andromeda possess roughly equivalent masses, 4 trillion solar masses each. 2 galactic superpowers on a cosmic collision course. Increased mass also influences our developmental history. Galaxies augment their size by consuming smaller celestial bodies. The larger you are, the more you have assimilated. A galaxy weighing 4 trillion solar masses possesses a violent past. We have devoured hundreds of dwarf galaxies, possibly thousands. Every satellite stream within the halo serves as evidence of a past meal. A galaxy that ventured too close paid the ultimate price. The Sagittarius dwarf galaxy is currently undergoing consumption. It is being dismembered, assimilated, its constituent stars dispersed throughout the Milky Way's disk. In a few 100 million years, no discernible trace of it will remain, save for spectral echoes within the data. This is the mechanism by which galaxies grow. Intergalactic cannibalism, the construction of galactic empires. But here lies the disconcerting reality. If we comprise 4 trillion solar masses, and the majority of that is dark matter, then we inhabit a galaxy composed primarily of intangible matter. 90% of our surroundings consists of something we cannot perceive, cannot physically interact with, cannot directly detect. You believe you are cognizant of your dwelling place. You believe you comprehend your cosmic environs. You are mistaken. You are immersed in an ocean of dark matter, yet you cannot sense the fluid. 4 trillion solar masses of predominantly invisible material. That is our home. That is the Milky Way. And we have only just begun to grasp its true immensity. The galaxy does not cease at the point where the stars diminish. It extends progressively further, far beyond anything visible, into the domain of pure dark matter. Scientists designate this the dark matter halo. A colossal, spherical envelope of invisible particles encircling the entirety of the visible galaxy. This halo is not a minor appendage. It is the predominant structure, the bedrock, the containment system that binds everything together. Conservative estimates place the halo's radius at 250,000 light-years. This is the viral radius, the boundary within which matter is gravitationally tethered to the galaxy. However, some theoretical models propose that the halo extends considerably further, 400,000 light-years, 600,000 light-years. Certain calculations extended beyond 1 million light-years. 1 million light-years. If this holds true, it renders the Milky Way 20 times wider than prior textbook estimations, 20 times more spatial dominion under our gravitational influence. Visualize the scale. Andromeda is situated 2.5 million light-years away. If our dark matter halo extends 1 million light-years outwards, and Andromeda's halo does likewise, a mere 500,000 light-years of truly empty space separates us. The halos might already be in contact, two invisible clouds of dark matter intermingling, merging, presaging the ultimate convergence. We cannot directly perceive the halo. Dark matter does not emit light, nor does it absorb light, nor does it interact with electromagnetic radiation in any manner. Its sole mode of interaction is gravitational. Yet, that gravitational influence is tangible, measurable, and potent. Researchers map the halo through indirect methodologies. The orbital trajectories of satellite galaxies reveal concentrations of mass. Gravitational lensing delineates areas where spacetime is distorted. Computational simulations predict the distribution of dark matter based on galactic morphology. You are currently situated within the halo. Dark matter surrounds you, passing through you. Earth is traversing a sea of dark matter particles moving at hundreds of miles per second. Trillions of them stream through your very being every second. You perceive nothing. They pass through ordinary matter as if they were phantoms. Scientists are endeavoring to detect dark matter directly. Deep subterranean laboratories await the rare instance of a dark matter particle colliding with an atomic nucleus. Thus far, no success. The particles may be too elusive, too infrequent, or our detection methods may be misaligned. If the halo truly extends 1 million light-years, the Milky Way claims an immense volume of space. The majority of our local galactic group falls within our sphere of influence. We are not merely a galaxy. We are a galactic dominion, a superstructure of unseen mass that dominates our surroundings. And if our halo is this extensive, then every other galaxy possesses one as well. The universe is not primarily vacant space punctuated by galaxies. The universe consists predominantly of dark matter halos, with galaxies embedded at their cores, like seeds within fruit. All that we observe is a minuscule fraction of existence. The visible universe is mere ornamentation upon an invisible framework. 1 million light-years of darkness. That is the Milky Way. That is home. And we are only at the nascent stages of comprehending its true immensity. The galaxy is rotating at an excessive velocity. It ought to disintegrate. Stars situated at the outer periphery orbit at speeds that defy logic. They should be propelled into intergalactic space. They ought to adhere to Kepler's laws of celestial motion. Their speed should diminish as one moves further from the center. This is not the case, and the precise reason remains largely unknown. Herein lies the quandary. Within our solar system, planets situated further from the Sun orbit at slower velocities. Mercury completes its circuit in 88 days. Earth requires 365 days. Neptune takes 165 years. The greater the distance from the Sun, the weaker its gravitational pull, and consequently, the slower the orbital velocity. This is fundamental physics. Isaac Newton elucidated this principle 3 centuries ago. Galaxies should operate on the same principle. The majority of the mass resides near the core. Stars situated further out should experience diminished gravitational attraction. Their orbits should consequently slow down. When their velocities are measured, one should observe a discernible curve that decreases with increasing distance. Except, this is not what transpires. Stars at the galactic periphery orbit at approximately the same velocity as stars situated closer to the center. The rotation curve remains remarkably flat. This is scientifically impossible unless there exists a greater quantity of mass in that region than is visually apparent. Dark matter. It is invariably dark matter. The invisible halo provides the supplementary mass. It extends far beyond the visible stars, maintaining the rapid motion of peripheral objects. The flat rotation curve serves as conclusive evidence. It is the definitive proof of dark matter's existence in colossal quantities. However, this is where the situation becomes peculiar. Even when accounting for dark matter, the observed velocities are higher than predicted. Some stars in the outer halo attain speeds of 130 km per second. Others reach 150 km per second. These velocities are marginally below escape velocity. The stars are nearly propelled with sufficient force to depart the galaxy entirely. Why do they orbit so precariously close to the threshold of escape? What finely tuned mechanism governs their confinement, yet maintains them at such a tenuous boundary? This phenomenon is termed the escape velocity problem, and it poses a persistent enigma for astronomers. One potential explanation is that our estimations of the galaxy's mass are still underestimated. Perhaps there is an even greater abundance of dark matter than current models propose. Possibly, the halo is denser at its extremities than we currently comprehend. It is conceivable that our mass calculations remain inaccurate. Another possibility is that the galaxy has undergone recent expansion. If the Milky Way has assimilated a substantial dwarf galaxy within the past few billion years, the merger could have injected stars into high-velocity orbits. These stars have not yet had sufficient time to settle into stable trajectories. They still retain the kinetic energy from the collision. Evidence lends credence to this hypothesis. The Sagittarius dwarf galaxy is presently being dismembered. Its constituent stars are being dispersed into the Milky Way's halo at considerable speeds. In 1 billion years, these stars will present as indigenous halo stars, swift, barely gravitationally bound, enigmatic. But what follows is even more extraordinary. Some stars exhibit excessively slow velocities. These are akin to hypervelocity stars in reverse. They are objects that, based on their location, should orbit at a higher velocity, yet do not. They drift languidly, as if ensnared in viscous fluid. No satisfactory explanation exists for these anomalies either. The rotation curve ought to be straightforward. Measure velocities, calculate mass, and everything should align harmoniously. Instead, every new measurement uncovers further deviations, more outliers, more stars behaving in ways that defy conventional expectations. This is the arena where dark matter theories are rigorously tested. Diverse models predict distinct rotation curves. Warm dark matter generates smoother profiles. Cold dark matter produces more aggregated structures. Self-interacting dark matter exhibits different behaviors within galactic cores. Thus far, cold dark matter aligns most closely with observations. However, the correspondence is not flawless. Discrepancies persist. Minor ones, nagging ones, the sort that might indicate novel physical principles, or could simply be attributable to measurement inaccuracies. The galaxy rotates with a velocity exceeding theoretical predictions. Stars orbit at speeds that elude simplistic explanations, and the increased galactic dimensions exacerbate the problem. A larger volume implies more space, more stars, and more anomalous velocities requiring elucidation. Physics functions universally across the cosmos. It operates within solar systems, star clusters, and distant galaxies. Yet, within our immediate vicinity, in the rotation curve of the Milky Way, something remains fundamentally incongruous. The Milky Way possesses 4 major spiral arms, or perhaps 5, or even 6. Astronomers are still engaged in debate. For decades, the established answer was 4 arms: Scutum Centaurus, Norma, Cygnus, Perseus, Sagittarius. Each arm is a vast current of stars, gas, and dust spiraling outward from the galactic nucleus. These arms delineate regions where new stars are actively forming. They are luminous, dense, and readily observable. Subsequently, superior telescopic instruments became available. Infrared instruments capable of penetrating dust clouds. Radio telescopes designed to map hydrogen gas distribution. Space-based observatories positioned above atmospheric distortions. Each new instrument unveiled features previously overlooked. The far 3 kiloparsec arm emerged first. A subordinate spiral arm concealed behind the galactic core. It was invisible to optical telescopes due to obstruction by the galactic center, but infrared instruments successfully penetrated the dust veil. There it was, an entire arm stretching for thousands of light years, directly beneath our observation. Subsequently, hints of other structures materialized. The local arm, where our solar system is situated, might actually be a primary arm, rather than a mere minor protrusion. New observations suggest it connects to more extensive formations further out. What we perceived as a branch could potentially be an entire limb. The outer arm presented another enigma. It is located at the extreme periphery of the visible galaxy. Some researchers posited it consisted merely of scattered stellar remnants, devoid of any coherent structure. However, detailed mapping revealed organized spiral patterns extending significantly into the outer regions. The galaxy exhibits structure where we previously presumed emptiness. But here lies the truly perplexing aspect. The mechanism responsible for the formation of spiral arms remains poorly understood. We observe them in nearly all disk galaxies. These are elegant, beautiful spirals, yet the underlying physics remains elusive. Herein lies the problem. Stars orbit the galactic center at varying velocities. Inner stars orbit more rapidly. Outer stars orbit more slowly. If spiral arms were simply aggregations of stars, they would progressively wind tighter and tighter over time, akin to stirring cream into coffee. Within a few rotations, the arms should dissipate into a uniform disk. This does not occur. Spiral arms persist for billions of years. This suggests they are not material structures, but rather density waves. These are regions where stars temporarily congregate, creating the visual impression of an arm, similar to vehicles bunching up in a traffic congestion. The vehicles move through the jam, but the jam itself remains stationary. The density wave theory is mathematically sound, but observational data consistently reveals anomalies. Certain arms exhibit an excessive number of young stars. Others display voids where stars ought to be present. The outer arm appears too massive to be solely a density wave. It may represent genuine structure, material ejected during a galactic collision millions of years ago. The increased size of the Milky Way further complicates matters. A larger volume provides more space for structural development. Arms can extend to greater distances. New arms can emerge in regions previously considered devoid of structure. The spiral pattern becomes more intricate. Recent surveys conducted by the Gaia spacecraft have meticulously mapped 1 billion stars with exceptional precision. The data revealed substructure within the arms, including branches, spurs, and gaps. The spiral pattern is not pristine. It is chaotic and disorganized, resembling tree branches extending in multiple directions. Some researchers now contend that the Milky Way is not a grand design spiral at all. It might be a flocculent spiral, a galaxy characterized by patchy, ill-defined arms. This would explain the variation in arm counts observed by different surveys. Each observer identifies distinct features contingent upon their measurement parameters. the debate continues. More advanced telescopes, more comprehensive data, and increased discussions at scientific conferences. However, one certainty remains. The Milky Way is far more complex than the simplistic four-arm depiction presented in textbooks. Hidden structures permeate the galaxy, including arms that have eluded detection for decades. And if we have overlooked entire spiral arms within our own galaxy, what other features might have gone unnoticed? What other formations lie concealed in the darkness, awaiting the revelation of the appropriate instrument? Draw a line delineating the galaxy's boundary. It sounds straightforward, yet it is an impossibility. Galaxies lack definitive borders like countries or continents. There is no cosmic border wall, no signpost announcing your departure from the Milky Way. Stars simply diminish in density gradually, eventually tapering off to none, or perhaps a few scattered stragglers. At what precise point does it cease to be considered part of the galaxy? This is not a purely philosophical inquiry, it is a practical challenge. Astronomers require a standardized definition, a consistent measurement, a method for comparing galaxies. However, nature does not conform to our dictates. The universe remains indifferent to our need for discrete classifications. Several definitions exist, none of which are entirely satisfactory. The optical radius marks the extent where visible stars become too faint to be detected. This delineates the luminous disk, the readily apparent portion, measuring 100,000 light-years for the Milky Way. However, this definition omits all faint stars, dim dwarf galaxies, and dispersed halo objects. It is akin to measuring a city by counting only skyscrapers and disregarding all residential structures. The viral radius offers a more scientific delineation. It signifies the boundary within which objects are gravitationally bound to the galaxy. Inside this radius, stars orbit the galactic center. Outside, they drift unimpeded. For the Milky Way, this yields a radius of approximately 250,000 light-years. This is a significant improvement. However, even this definition presents challenges. Some stars located beyond the viral radius still exhibit orbital motion consistent with the galaxy's overall movement. They share our trajectory through space. They originated within our galaxy. Do they constitute part of the galaxy or not? The viral radius indicates they do not. Common sense suggests a potential inclusion. Furthermore, there is the dark matter halo. It extends considerably beyond all other defined boundaries. If the halo reaches 1 million light-years outward, does that constitute the true edge? The majority of astronomers would answer in the negative. The halo dissipates so gradually that designating any specific boundary becomes arbitrary. It is comparable to attempting to pinpoint the termination of Earth's atmosphere. Technically, it extends thousands of miles upwards. Practically, it becomes imperceptible beyond 100 miles. Where does one draw the line? The situation becomes more complex when considering galactic winds. The Milky Way expels massive outflows of gas. Supernovae detonate. Stars shed material. This expelled gas propagates outward into intergalactic space, extending hundreds of thousands of light-years. Is this material still considered part of the galaxy? Some of it will eventually return. Gravity exerts its pull, drawing it back inwards. The galaxy recycles its gaseous components over billions of years. However, some of it escapes permanently, lost to the void. At what juncture does gas cease to be Milky Way gas and transition into the intergalactic medium? The Magellanic Stream introduces further complication. The large and small Magellanic Clouds are shedding gas as they orbit us. This ejected gas forms a trailing stream that stretches across the celestial sphere. Does this stream belong to the Magellanic Clouds, to the Milky Way, or neither? All three classifications have their proponents. Andromeda presents a similar challenge from the opposing direction. Its dark matter halo might already be in contact with ours. When two halos overlap, where does the boundary of one galaxy end and the other begin? The intervening space becomes shared territory, co-owned, contested. This is not merely a semantic quibble. The definition impacts mass estimations. It influences comparisons of galactic size. It affects our understanding of when the Andromeda collision will truly commence. If the halos are already merging, the collision began millions of years ago. We are currently living through it. Most astronomers adopt practical definitions. The disk terminates where star formation ceases. The halo ends at the viral radius. The dark matter extends as far as simulation models suggest. Each definition serves distinct analytical purposes. None of them perfectly encapsulate the entirety of reality. Herein lies the truth. The Milky Way is not a discrete object. This is a territory, a sphere of influence, a celestial neighborhood. It possesses a concentrated core, a middle ground with structure, and an indistinct periphery. Beyond that edge, it dissolves into something else entirely. 200,000 light-years represents our most accurate current estimate. However, re-examine that figure in a decade. Refined measurements will alter it. They invariably do. The galaxy lacks a definitive boundary because the cosmos does not function in such a confined manner. Everything intermingles. Everything is interconnected. We inhabit a universe devoid of strict divisions, and we are still in the process of quantifying it. There are stars situated at the extreme edge of the galaxy traveling at astonishing velocities, 130 meters per second, 150. Some reach speeds of 200. They ought to break free. They should hurtle into the void between galaxies. They do not. Something restrains them. These are identified as high-velocity halo stars, distinct from hypervelocity stars, which possess sufficient speed to escape. Halo stars move just below that critical speed, precariously tethered, poised on the brink of liberation. Their detection proved challenging. They are faint, distant, and dispersed across an immense volume. Yet, observational campaigns like Gaia meticulously track millions of stars with remarkable precision, capturing their positions, charting their movements, and calculating their velocities. Certain stars immediately raise red flags. One star traversing the outer halo is moving at 198 meters per second. The galaxy's velocity required for escape at that particular location approximates 200 meters per second. This star is merely 2 meters per second away from permanent departure. It resembles a rocket on the verge of being released from Earth's gravitational hold. A minuscule nudge, and it would be gone. Why do so many stars orbit at speeds so close to the escape velocity? This is not a matter of random chance. Something has placed them there. Something has imparted that precise amount of kinetic energy. But what is that something? Galactic mergers offer a potential explanation. When the Milky Way assimilated smaller galaxies, these collisions injected kinetic energy into the system. Stars originating from the dwarf galaxy receive substantial velocity boosts. Some managed to escape, while others settled into swift, barely bound orbital paths. These survivors now populate the halo. The Sagittarius dwarf galaxy provides compelling evidence. Its stars are dispersing at high velocities, as the Milky Way gradually dismantles it. Within 1 billion years, those stars will be indistinguishable from other halo stars, swift, ancient, and enigmatic. But we have observed this one in the midst of the process. We are witnessing it unfold. Another plausible scenario involves interactions between 3 celestial bodies. When 2 stars pass in close proximity to a third object, gravitational forces can propel one of the stars outward at considerable speed. This phenomenon occurs within dense stellar clusters. Occasionally, a star is ejected with enough energy to reach the galactic halo. Most escape entirely. A select few find themselves in that ideal position, moving rapidly, but not excessively so. Black holes introduce an element of complexity. If a star ventures too near a supermassive black hole, the gravitational slingshot effect can accelerate it to extraordinary velocities. The supermassive black hole at the galaxy's core possesses a mass equivalent to 4 million suns. Any star that approaches too closely is either consumed or violently expelled. We have identified several hypervelocity stars, departing the galaxy at speeds exceeding 400 meters per second. These stars are unequivocally escaping. Calculations trace their trajectories back to the galactic center. Something in the vicinity of the black hole propelled them outward. It is possible they were part of binary systems, and the black hole captured one star while ejecting the other. However, the barely bound stars present a different enigma. They are not originating from the galactic core. They orbit in the far reaches of the halo. Their velocities are high, yet not extreme. They appear to be comfortably situated at the periphery of the galaxy's gravitational influence. One hypothesis posits that the dark matter halo is less uniform than we currently believe. Concentrations of dark matter at specific distances could generate stable orbital paths at elevated velocities. Stars would naturally settle into these configurations. This would account for the similar velocities observed among many halo stars. They are essentially locked in orbital resonance with the dark matter distribution. Verifying this hypothesis is challenging. We cannot directly perceive dark matter. Our inferences about its distribution are solely based on stellar motions. Nevertheless, if the halo possesses localized density variations, we would expect to observe groupings, clusters of high-velocity stars moving in concert. Some surveys offer hints in this direction. Others indicate random arrangements. The available data is somewhat equivocal. What we ascertain with certainty is that the outer reaches of the galaxy exhibit more dynamism than anticipated. Stars are moving at speeds that exceed predictions from simpler models. The demarcation between being gravitationally bound and unbound is exceedingly narrow. A difference of mere miles per second separates perpetual adherence from outright departure. If the galaxy extends further than our current estimations, a greater number of stars reside within this precarious zone. More objects are poised at the precipice. More potential escapees. And comprehending the reasons for their continued presence offers profound insights into galactic architecture, the nature of dark matter, and the workings of gravity on vast scales. Swift stars at the galaxy's periphery, held in place by unseen mass, traversing at velocities that seem improbable. And we are only beginning to unravel the mysteries of what retains them. The Milky Way is not an anomaly. If our measurements of our own galaxy are imprecise, then our assessments of all galaxies are likely flawed. This is the unsettling implication, the realization that compels astronomers to dedicate sleepless nights to recalculating their established understanding. Every galaxy in the observable universe might be twice the size we have recorded. The celestial census requires a comprehensive revision. This is why this matter is significant. Astronomers utilize galaxies as tools to comprehend the universe, to understand the distribution of matter, the formation of structure, and the influence of dark energy on cosmic expansion. If galaxies are all larger than we previously surmised, every calculation undergoes alteration. Galactic masses dictate their interactions. More massive galaxies exert stronger gravitational pulls. They more readily strip stars from their smaller neighbors. They exert greater dominance over their local galactic groupings. They assemble into clusters in distinct ways, necessitating a recalculation of masses and, consequently, a reevaluation of galactic evolution. This challenge extends to the determination of distances. Astronomers employ certain types of galaxies as cosmic distance markers, objects with a known intrinsic brightness. By measuring their apparent brightness, they can infer their distance. However, if these galaxies are larger, their brightness is subject to change, and consequently, their distances are also altered. This, in turn, affects the calculated expansion rate of the universe. Measurements of dark energy are contingent upon precise distance calculations. Any error introduced will propagate through all cosmological models. If galaxies are universally larger, calculations pertaining to dark energy will be adjusted, potentially indicating that the universe is expanding at a rate faster or slower than our current estimations suggest. Researchers are presently re-examining existing galaxy surveys, including the Sloan Digital Sky Survey and the 2-micron All-Sky Survey, along with every other major catalog. They are implementing novel measurement techniques, taking into account dark matter halos, and utilizing stellar streams and satellite galaxies where applicable. Preliminary findings are concerning. Numerous galaxies appear larger, with some exhibiting a 50% increase in size, while others are twice as large. The trend is consistent. We have systematically underestimated galactic dimensions. The Andromeda Galaxy is larger than previously thought. The Triangulum Galaxy is also larger. Every significant galaxy within our local group necessitates a remeasurement. And if local galaxies are indeed larger, it is highly probable that distant galaxies are as well. The entire cosmic web may be more densely populated than we have realized. This has implications for our understanding of dark matter. If galaxies are larger, they contain a greater quantity of dark matter. The ratio of dark matter to ordinary matter is therefore altered. This impacts theories concerning galaxy formation. It influences predictions regarding the evolutionary trajectory of the universe. It raises questions about the fundamental validity of our cosmological models. Some researchers propose that this discrepancy could resolve long-standing astronomical puzzles, such as the missing satellite problem. Simulations predict that large galaxies should be orbited by hundreds of satellite galaxies. However, we observe only dozens. If our galaxy is larger, its gravitational reach extends further. It is conceivable that these missing satellites exist but orbit at such great distances that they have evaded detection. Another intriguing puzzle relates to galaxy rotation curves. Many galaxies exhibit a rotation pattern similar to that of the Milky Way, characterized by a remarkably flat velocity profile. Stars at the outer edges orbit at unexpectedly high speeds. This phenomenon was the initial impetus for hypothesizing the existence of dark matter. However, if galaxies are larger, their dark matter halos extend further outward. The observed rotation curves become more comprehensible. The underlying physics aligns more coherently. Nevertheless, this revised understanding introduces new challenges. If galaxies are larger, the space separating them is reduced. The universe consequently becomes more crowded. Galactic interactions occur more frequently. Collisions transpire sooner. The timeline of cosmic evolution accelerates. This has a direct impact on our understanding of galaxy clusters, which are vast aggregations of galaxies bound by gravitational forces. If each individual galaxy is larger, their gravitational interactions become significantly more complex. The dynamics of the cluster are altered. Mass estimations must be revised. Dark matter distributions require recalculation. Even the very early stages of the universe are affected. Astronomers study cosmic history by observing distant galaxies that formed billions of years ago. If those primordial galaxies were larger than measured, they must have formed more rapidly than our current models suggest. Structure assembly would have occurred more swiftly. The universe would have been more developed at earlier epochs than our models indicate. These implications ripple through every branch of astronomy, including studies of stellar populations, galaxy morphology, active galactic nuclei, and the evolution of supermassive black holes. Everything is intrinsically linked to galactic size. We are undertaking a reevaluation of the universe, re-examining every galaxy, every cluster, every structure, commencing anew with enhanced measurement capabilities. And the universe that is emerging is larger, denser, and more intricate than we had previously envisioned. The Milky Way served as the initial impetus, the first domino to fall, and the rest are now following suit. The Milky Way rotates around a specific point, not the supermassive black hole, nor the visible galactic center, but its center of mass. And we have only recently come to understand that this point is not situated where we had originally presumed. The concept of the center of mass is fundamentally straightforward. It represents the point of equilibrium, the location where all the mass is effectively averaged. For a simple rod, it is its midpoint. In the Earth-Moon system, it is a point situated within the Earth, offset from its geometric center due to the Moon's gravitational influence. For a galaxy, it is the pivotal point around which all its constituents orbit. Astronomers had historically assumed that the center of mass coincided with the galactic core. This assumption seemed logical, as the majority of visible stars are concentrated there, and the supermassive black hole resides at that location. Everything appeared to point towards the core. However, this assumption neglected the significant contribution of dark matter. Dark matter does not exclusively concentrate in the galactic core. Instead, it forms an expansive halo encompassing the entire galaxy. This halo is not perfectly uniform. It exhibits localized variations in density, with some regions being more concentrated and others more diffuse. The distribution of dark matter consequently shifts the galaxy's overall center of mass away from its visible center. Upon recalculating, incorporating the revised understanding of galactic size and updated dark matter distributions, scientists discovered that the center of mass had indeed shifted. While not a dramatic displacement of thousands of light years, it is a significant enough alteration to have consequences. The shift amounts to a few hundred light years, perhaps extending to 1,000 light years. This may sound negligible. However, in human terms, it is an immense distance. The center of mass has shifted further than the entire distance separating Earth from its nearest stellar neighbor, and further than dozens of solar systems arranged end to end. Why does this distinction matter? All celestial objects orbit the true center of mass, not merely the visible center. Stellar orbital paths are directly influenced by the location of this pivotal balance point. Satellite galaxies revolve around this same center. The precise velocities of stars situated near the galactic core provide crucial data for pinpointing the center of mass. Measuring this displacement is an intricate task. It requires highly precise velocity data for stars distributed throughout the galaxy. Accurate maps detailing the distribution of dark matter are essential. Sophisticated computer simulations are necessary to model the galaxy's entire gravitational field. Only recently have our observational instruments achieved the requisite sensitivity to detect this subtle offset. The Gaia spacecraft has been instrumental in this breakthrough, meticulously measuring the positions and velocities of over 1 billion stars with unprecedented accuracy. Researchers have integrated this data into simulations, enabling the calculation of the gravitational center. The findings have been surprising. The calculated center of mass does not precisely align with the position of the supermassive black hole. This has significant implications for our own orbit. The solar system completes a circuit around the galactic center approximately once every 230 million years, a period known as a galactic year. However, if the center of mass is offset, our actual orbital path deviates slightly from previous calculations. We might complete an orbit marginally faster or slower than initially determined. This offset also influences how we model the galaxy. For computational simplicity, simulations typically assume perfect symmetry, positing a central core and a uniformly distributed dark matter halo around it. However, reality is far more complex. The Milky Way likely formed through the amalgamation of smaller galaxies. These past collisions have left lasting imprints. Asymmetries in the dark matter distribution result in offset concentrations of mass. The Sagittarius dwarf galaxy is currently in the process of being incorporated into the Milky Way. As it disintegrates, its mass exerts a gravitational influence, albeit a minor one, on our galaxy's overall center of gravity. The dwarf galaxy is comparatively small in relation to the entire Milky Way. However, over timescales spanning millions of years, these interactions cause the balance point to shift. Some researchers propose that the center of mass undergoes oscillatory motion, subtly migrating back and forth as galaxies are absorbed and assimilated. The Milky Way is not a static entity. It is a dynamic system, in constant evolution, perpetually consuming matter, and each act of consumption alters the delicate balance. The most peculiar aspect of this discovery is its implication for the supermassive black hole itself. If the center of mass is offset from the black hole, why is the black hole located where it is? Supermassive black holes are presumed to reside at galactic centers because they originate there. They grow by accreting material that drifts towards the center of mass. If the center of mass is situated elsewhere, it raises the question of the black hole's current location. One plausible explanation is that the black hole predates the current galactic structure. It may have formed when the galaxy was smaller and possessed a more symmetrical mass distribution. As the Milky Way grew through mergers, the distribution of its mass changed. The center of mass migrated, but the black hole, being exceedingly massive, remained fixed in its position. An object with a mass of 4 million solar masses cannot be easily displaced. Another possibility is that the current offset is a temporary phenomenon. Over billions of years, the galaxy is expected to achieve a more symmetrical configuration. The center of mass will gradually drift back towards the core, and the black hole will remain at the center, restoring equilibrium. However, at this particular juncture in galactic evolution, the balance point is slightly askew. The Milky Way rotates around a point that is not precisely where we had anticipated. The galaxy has simply become larger. And with this expansion has come a shift, a subtle alteration in the very center of existence. Though diminutive in cosmic terms, it is immense from a human perspective. And we are only beginning to comprehend the full implications of this shift. Galactic collisions are not the dramatic events often depicted. They involve no explosive phenomena, no fiery cataclysms, no abrupt impacts, but rather a slow-motion gravitational ballet that unfolds over hundreds of millions of years. However, the scale of the interacting galaxies fundamentally alters the outcome. A larger galaxy engages in collisions differently than a smaller one. The underlying physics remain consistent, but the resulting consequences are entirely transformed. When two diminutive galaxies interact, the process is relatively swift, spanning a few 100 million years, perhaps a billion. They merge, stabilize, and proceed independently. But when two colossal galaxies, such as the Milky Way and Andromeda, collide, the duration of this process extends considerably. The increased mass translates to a stronger gravitational pull. This intensified gravity leads to more intricate interactions. Here is a depiction of what transpires during the collision of two massive galaxies. The initial contact occurs when their respective dark matter halos begin to overlap. This event precedes any interaction between their visible stellar disks. These halos extend hundreds of thousands of light-years outward. Upon meeting, gravity commences its work. The halos interpenetrate. Dark matter particles, behaving akin to spectral entities, pass through one another. They do not physically collide. They do not rebound. They simply coexist within the same spatial volume. However, their gravitational influence affects all surrounding matter. Stars experience gravitational pulls from both galactic centers, leading to the destabilization of their orbits and the onset of chaotic dynamics. Subsequently, the outer stellar halos interact. Stars within these regions are already moving at considerable velocities, existing in a state of precarious gravitational confinement. As another massive galaxy approaches, some of these stars are propelled into intergalactic space, ejected permanently from their original galactic systems. Others are captured by the approaching galaxy, effectively stolen. The galaxies begin to exchange stellar populations, much like trading cards. Following this, tidal forces come into play. As the galaxies traverse past each other, the gravitational pull exerted on the near side of each galaxy is stronger than that on the far side. This differential force stretches both galaxies, drawing material outward into elongated streamers known as tidal tails. These tails can extend millions of light-years into space, serving as beautiful yet destructive testament to the immense forces at play. The visible disks finally collide. When they meet, a remarkable phenomenon occurs. The vast gas clouds within both galaxies are compressed. Compressed gas undergoes gravitational collapse. Collapsed gas subsequently forms new stars. Star formation erupts across both galaxies, igniting millions of new stars in a spectacular cosmic display. Astronomers refer to these events as starburst galaxies, indicative of ongoing collisions. However, it is at this juncture that size becomes paramount. Larger galaxies possess deeper gravitational wells, making it more difficult for matter to escape. When material is drawn into tidal tails, a greater proportion of it eventually falls back towards the galaxy. Smaller galaxies tend to lose material permanently, whereas larger galaxies recycle it. During their collision, the Milky Way and Andromeda will shed stars, but the majority will eventually return. Furthermore, the timeline for the merger extends significantly. Small galaxies may complete their merger after 1 or 2 close passes. Large galaxies, however, orbit each other multiple times. 3 passes, 4, possibly even 5, each pass stripping away more material and drawing their cores progressively closer. Eventually, friction generated by interactions between gas and stars dissipates orbital energy. The galaxies spiral inward, and their cores merge. The ultimate form of the resultant galaxy depends on the mass ratio of the colliding entities. When 2 galaxies of comparable mass collide, the outcome is typically a massive elliptical galaxy. The original spiral structure is entirely obliterated, and the stars from the disks are scrambled into chaotic, random orbits, eradicating any semblance of elegant spiral arms in favor of a more amorphous stellar distribution. Milta, the future merged entity of our galaxy and Andromeda, will be colossal, containing an estimated 800 billion stars and possessing a mass of 4 trillion solar masses, establishing it as one of the most massive galaxies in the local group, a true heavyweight. However, this collision also triggers other significant effects. The supermassive black holes at the centers of each galaxy will eventually merge. The 4 million solar masses of the Milky Way's black hole combined with the 1 billion solar masses of Andromeda's black hole will result in a single, exceptionally massive black hole at the heart of Milomea. This merger event will unleash gravitational waves detectable across the entire observable universe. Star formation will experience a dramatic surge, followed by a subsequent decline. The initial collision ignites millions of new stars, but the merger process consumes the majority of the available gas reserves. After a period of several billion years, star formation will cease entirely. Milkomea will transform into a red and quiescent galaxy, populated by old stars with no new star formation, gradually fading over time. Larger galaxies engage in collisions differently, characterized by extended timelines, more complex interactions, and more profound outcomes. And we are currently witnessing the preliminary stages of this celestial drama. The Milky Way and Andromeda have already begun their intricate orbital dance. Their dark matter halos may already be in contact. The first physical interaction may have already transpired. The collision is not an impending event. It has already commenced, and the scale of the involved galaxies dictates the ultimate narrative. There exists a quantity of mass that we cannot account for, material that should be present but is inexplicably absent. Astronomers refer to this as the missing mass problem, and this enigma has just escalated threefold. The core of the issue lies in the following observation. When all the observable matter within a galaxy is aggregated, it amounts to approximately 200 billion solar masses, encompassing stars, planets, gas clouds, dust, and all other detectable components. However, theoretical models based on cosmological principles dictate that galaxies should contain a specific proportion of baryonic matter, determined by the cosmic ratio. Yet, when we tally the stars, gas, and dust, our count falls significantly short. Indeed, roughly half of the expected baryonic matter appears to be missing. The question arises, where has this matter vanished? Several potential explanations exist. The first theory suggests that the missing baryonic matter has been expelled from the galaxy. Supernovae explosions, powerful stellar winds generated by stars, and energetic outflows from active galactic nuclei can collectively eject substantial amounts of material. Over billions of years, this outflow could have propelled vast quantities of gas into intergalactic space. In this scenario, the baryonic matter is not truly missing. It simply resides outside the galactic boundary, too diffuse to be readily detected. The second theory proposes that the missing baryons are in hiding. They might exist as cold gas clouds that are too faint to be observed, or as dim brown dwarfs too small to emit significant light, or as rogue planets drifting through interstellar space. In this view, the matter is present, but current observational instruments are insufficient to detect it. The third theory ventures into more speculative territory. Perhaps the baryonic matter was never within the galaxy to begin with. It might reside within the intergalactic medium, the tenuous space between galaxies. This medium contains extremely diffuse gas. However, when considered across vast cosmic volumes, the cumulative mass can be substantial. It is conceivable that half of the universe's baryonic matter is dispersed within this medium, never having fallen into galaxies. Recent observational evidence lends stronger support to the first theory. X-ray telescopes have detected the presence of hot gas halos surrounding galaxies, suggesting a significant reservoir of baryonic matter extending beyond the visible confines of galactic disks. This particular celestial material, incredibly hot and lacking sufficient density for stellar formation, exists in a peculiar intermediate state. It's ionized and energetic, rendering it practically invisible to most detection instruments. Nevertheless, it is present in substantial quantities. When scientific observers quantified these heated outer regions, they discovered a significant amount of mass, enough to account for a considerable portion of the universe's purportedly missing baryonic matter. This revelation suggested a potential solution to the cosmic puzzle. However, the expansion of the Milky Way implies an even greater abundance of baryonic matter, and the challenge of locating it all persists. A galaxy possessing a mass equivalent to 4 trillion suns necessitates a specific proportion of ordinary matter, dictated by cosmic ratios. This translates to approximately 400 billion solar masses of baryons. Current observations reveal perhaps 200 billion solar masses within stars and gas. The remainder remains unaccounted for. Consequently, tripling the galactic mass exacerbates the missing mass conundrum by a similar factor. If the galaxy has doubled in width and gained substantial mass, where has all the surplus baryonic material vanished? It should reside somewhere within the galactic halo or disk, in orbit, yet it eludes detection. Some researchers posit that the dark matter halo acts as a trap for superheated gas at immense distances, extending hundreds of thousands of light years from the galactic center. This gas is so extraordinarily hot and diffuse that contemporary X-ray telescopes can barely register its presence, yet it embodies considerable mass. Future observational missions, equipped with enhanced sensitivity, may unveil vast reservoirs of elusive baryonic matter concealed in plain view. Another plausible explanation involves the circumgalactic medium, the expansive zone encircling a galaxy where matter perpetually cycles in and out. Gas expelled by supernovae flows outwards, subsequently cools, and re-enters the galaxy. This continuous recycling process cultivates a substantial reservoir of baryons surrounding the galaxy, situated neither entirely within nor entirely outside its defined boundaries. The James Webb Space Telescope is actively engaged in the pursuit of these elusive baryons. Its advanced infrared detection capabilities enable it to perceive warm gas that other instruments overlook. Preliminary findings suggest a greater concentration of material in the outer halo than previously indicated by earlier surveys. Nevertheless, further data acquisition, enhanced observations, and extended research periods are imperative. The unsettling reality is that we inhabit a galaxy where a substantial fraction of ordinary matter cannot be accounted for. While the distribution of dark matter is roughly understood, ordinary matter, the fundamental constituent of all known life, continues to evade detection. An enlarged galaxy intensifies this mystery, amplifying the missing mass problem and perpetuating unanswered questions. Somewhere within the vast darkness, 400 billion solar masses of ordinary matter await discovery. The Milky Way is not an exceptional entity. This observation consistently emerges in astronomical research. Every instance where we perceive our galaxy as unique, we subsequently discover universal similarities. If our galaxy is indeed twice as extensive as previously estimated, then all spiral galaxies universally face a similar miscalculation. Researchers have rigorously examined this hypothesis. They meticulously selected a sample of nearby spiral galaxies, including Andromeda, Triangulum, and other galaxies close enough for detailed scrutiny. Subsequently, they applied novel measurement methodologies, incorporating satellite galaxy tracking, stellar stream mapping, and dark matter halo calculations. Astonishingly, every single galaxy examined proved to be larger than previously assessed, not by a marginal amount, but significantly, averaging 50% greater in size. Some galaxies exhibited a doubling in their dimensions, mirroring the recalibration of the Milky Way. This pattern demonstrated remarkable universality. We have systematically underestimated the sizes of spiral galaxies across the board. Andromeda serves as the most compelling illustration of this phenomenon. The prior estimation indicated a diameter of 220,000 light-years. However, contemporary calculations suggest a diameter of 300,000 light-years, possibly even more. The dark matter halo extends even further into space. Andromeda is a colossal entity, considerably more massive than initially conceived. Triangulum, the third largest galaxy within the local group, expanded from an estimated 60,000 light-years to nearly 100,000 light-years in diameter. Smaller galaxies exhibited comparable increases in size, such as NGC 524 and NGC 2976. Every spiral galaxy subjected to examination revealed a larger physical extent. The underlying cause for this discrepancy mirrors the error in our assessment of the Milky Way. Earlier measurement techniques predominantly relied on visible light. They focused on the luminous galactic disk where stars are concentrated, inadvertently disregarding the faint outer peripheries. Furthermore, they underestimated the gravitational contributions of dark matter. This inaccuracy was an intrinsic aspect of the methodology itself. The advent of modern observational instruments has revolutionized our understanding. Wide-field surveys now meticulously map entire galaxies from edge to edge. Infrared detectors penetrate obscuring dust clouds. Deep exposure imaging reveals exceedingly faint stars in the outer regions. Each incremental improvement effectively extends the measured radius outwards. However, the most profound breakthrough originated from the study of satellite galaxies. Just as the Milky Way is orbited by smaller satellite galaxies, other large spiral galaxies host similar companions. Andromeda is accompanied by dozens of dwarf galaxies. Triangulum possesses several. By meticulously tracking these satellites, analyzing their orbital paths, and calculating the gravitational mass that governs them, astronomers can ascertain the true dimensions of the host galaxies. Stellar streams have also become evident across the cosmic landscape. Andromeda is currently in the process of assimilating several smaller galaxies, resulting in prominent streams of stars that encircle it, akin to forensic evidence at a crime scene. These streams orbit far beyond the visible disk, substantiating Andromeda's gravitational influence extending to distances previously unconsidered by older measurements. Dark matter halos, in their entirety, extend far beyond initial predictions. When the full extent of these halos is factored in, rather than focusing solely on the dense inner regions, spiral galaxies reveal themselves as truly enormous structures. Their spheres of influence span hundreds of thousands of light-years. Consequently, the perceived distances between galaxies diminish proportionally. This groundbreaking discovery carries far-reaching implications. The frequency of galactic collisions requires recalculation. As galaxies increase in size, their surrounding halos overlap more frequently, leading to more common interactions. This suggests a more dynamic and potentially violent universe. The density of galaxies also undergoes revision. A given volume of space now accommodates fewer galaxies, given that each individual galaxy is larger. This shift significantly impacts cosmological models and fundamentally alters our comprehension of structure formation, as well as predictions regarding the evolution of galaxy clusters. Furthermore, rotation curves of spiral galaxies now exhibit greater coherence. Previously, many spiral galaxies displayed flat rotation curves, similar to the Milky Way, where stars at the outer edges orbited at unexpectedly high velocities. However, with the acknowledgement of larger galactic dimensions and more expansive dark matter halos, these rotation curves become far more consistent with established physical principles. Some researchers are investigating whether dwarf galaxies exhibit similar patterns. Initial findings suggest this is indeed the case, with even smaller galaxies appearing larger than previously measured, their dark matter halos extending further than their visible stellar components. This underestimation of size seems to affect galaxies across all scales. The situation with elliptical galaxies remains somewhat less clear. They lack distinct disks or spiral arms, making the precise determination of their boundaries even more challenging. However, preliminary investigations indicate that they too are larger than traditional estimates suggest. The observed phenomenon appears to be universal. The fundamental conclusion is that for decades, astronomers have employed incomplete methodologies when measuring spiral galaxies. They primarily cataloged what was readily observable, delineating boundaries where stars became indistinct. They operated under reasonable assumptions that have subsequently proven to be erroneous. Every spiral galaxy in the observable universe is demonstrably larger than depicted in current astronomical textbooks, not solely our own Milky Way, but all of them. This necessitates a comprehensive revision of the cosmic census. We are only just beginning to comprehend the true magnitude of these cosmic structures. The local group of galaxies has effectively shrunk, not in physical size, but in conceptual understanding. The expanse between galaxies has diminished due to the increased dimensions of the galaxies themselves. The local group represents our immediate cosmic neighborhood, a gravitationally bound collection of galaxies dominated by three colossal entities, the Milky Way, Andromeda, and Triangulum, along with dozens of smaller dwarf companions orbiting them. The total estimated population within a 10 million light-year radius was previously thought to be around 80 galaxies. However, these perceived boundaries now require redefinition. As galaxies grow larger, their gravitational influence extends further into space. The spheres of influence expand, and regions previously considered neutral intergalactic space are now recognized as belonging to one galaxy or another. the buffer zone between these galactic giants effectively shrinks. Andromeda is situated approximately 2.5 million light-years from Earth. The prior measurement indicated a separation of 2.5 million light-years of seemingly empty space between our visible galactic disks. However, with updated size estimations, this picture undergoes a significant transformation. Our own dark matter halo extends at least 250,000 light-years outwards, potentially further. Andromeda's halo exhibits a similar extension, possibly even greater. Subtracting the estimated extents of these halos from the total distance, 2.5 million minus 500,000, leaves only 2 million light-years of truly neutral space separating us, and this figure decreases further if the halos extend even more. Some models suggest that these halos may already be in contact, implying that collisions may have commenced within the unseen dark matter realm. This recalibration fundamentally alters our understanding of galactic group dynamics. The local group is no longer conceptualized as three distinct entities with intervening space. Instead, it comprises three overlapping spheres of gravitational influence, where boundaries blur and territories become subject to contention. Certain dwarf galaxies now appear to orbit within regions claimed by multiple large galaxies. Consider the Magellanic Clouds. Are they satellites of the Milky Way, or merely passing through? Previous estimations suggested they might eventually escape the Milky Way's gravitational pull. However, contemporary calculations indicate otherwise, asserting that our galaxy's gravity extends further, effectively trapping these clouds as permanent inhabitants. Within a few billion years, the Milky Way will fully assimilate them. Several dwarf galaxies are situated in the intervening space between our galaxy and Andromeda. Their allegiance is now ambiguous, technically orbiting within the combined gravitational field of both, experiencing gravitational pulls from multiple directions. As the Milky Way and Andromeda approach each other, these dwarf galaxies will become ensnared in the gravitational crossfire, potentially torn apart and scattered as casualties of an impending galactic collision. Triangulum faces a comparable destiny. It is the third largest galaxy in the local group, but only marginally, containing approximately 60 billion stars. New measurements suggest it may already be on a trajectory to fall into Andromeda. The distance between them is now only about 750,000 light-years. With the updated halo dimensions, they are virtually in contact. Triangulum is no longer an independent entity, but is effectively a satellite of Andromeda, or will be imminently. The redrawing of galactic boundaries impacts how we enumerate galaxies. Certain celestial objects previously considered independent are now reclassified as satellites, while others previously designated as satellites might be reevaluated as independent. The total number of galaxies within the local group remains approximately 80, but their categorization undergoes a significant alteration. The group's center of mass also shifts. Within large galactic sizes and updated mass estimations, the point of gravitational equilibrium moves. It now resides somewhere between the Milky Way and Andromeda, likely closer to Andromeda due to its potentially greater mass. This pivotal point dictates the future evolution of the entire group, influencing the orbits of all its members and their eventual trajectory towards the center. Beyond the local group, the boundaries with neighboring galactic clusters also require reassessment. The Sculptor group is situated approximately 12 million light-years away, while the Maffei group is closer but obscured by the disk of the Milky Way. These adjacent clusters possess their own distinct gravitational zones. As galaxies grow larger, these zones expand, consequently shrinking the space between clusters. Some astronomers now propose that the local group is more extensive than traditionally defined, potentially spanning 15 million light-years across instead of 10. Its outermost members orbit at greater distances than previously understood, and the group's gravitational dominion extends over a larger territory. This expanded influence is crucial for comprehending the overarching cosmic structure. Galaxy groups themselves aggregate into superclusters. The local group is a component of the Virgo supercluster, or possibly the larger Ionia Chaos supercluster, depending on how boundaries are delineated. If individual groups are larger, the structure of superclusters undergoes reorganization, causing shifts in the hierarchy of cosmic organization at every hierarchical level. The peculiar aspect of this situation is that boundaries are inherently arbitrary. Galaxies do not adhere to imaginary lines. They intermingle, overlap, and merge. The concept of distinct entities is a human construct. In reality, nature operates through continuous gravitational fields, smooth gradients of density, devoid of walls or borders. The local group should not be viewed as a collection of isolated galaxies, but rather as a singular, vast gravitational basin containing concentrated pockets of matter that we identify as galaxies. Regardless of how we redraw these boundaries, the underlying reality is far more complex and fluid than any map can accurately depict. We find ourselves living within this intricate tapestry, attempting to chart territories that inherently resist strict delineation. The stellar count has just doubled. The Milky Way galaxy now contains approximately 400 billion stars, possibly even more. Every previous estimate has been effectively doubled in conjunction with the revised galactic dimensions. The figure of 400 billion is, quite frankly, incomprehensible. If one were to count each star individually at a rate of 1 per second, it would require approximately 12,700 years to complete the task. This duration surpasses the entirety of recorded human history, and even then, billions of stars would remain uncounted. To put this into perspective, consider Earth's current population of 8 billion humans. It would require 50 times the current global human population to match the number of stars within this single galaxy, 50 entire planets populated by humans. This illustrates the sheer scale of stars we are discussing. Earlier estimations placed the number at 200 billion, but these were inaccurate. The error stemmed from sampling methodologies. Astronomers counted stars within small, localized regions, and then extrapolated these numbers to the entire galaxy. They measured the solar neighborhood, determining the number of stars per cubic light-year, and then multiplying this density by the galaxy's estimated volume. This approach was straightforward, except that the initial estimation of the galaxy's volume was incorrect. Doubling the galactic radius, for instance, increases its volume by a factor of 8. A galaxy twice as wide encompasses 8 times the spatial volume. While not all of this expanded volume is densely populated with stars, the outer regions, though sparse, still contribute significantly. Summing up, all this additional volume results in billions more stars. The majority of these newly accounted for stars are red dwarfs, which are small, dim, and possess exceptionally long lifespans. These stars constitute roughly 70% of all stars in the galaxy, yet they contribute minimally to the overall light output. A region containing a billion red dwarfs might still appear remarkably dark. They essentially hide in plain sight. The outer halo of the galaxy contains a greater number of stars than previously assumed. Older surveys failed to detect them due to their faintness and diffuse distribution. However, modern instruments with superior sensitivity are now revealing their presence. Hundreds of millions of halo stars orbit far from the main galactic disk. These are ancient stars, characterized by a low metallicity, survivors from the galaxy's earliest epochs. Additionally, we must consider the stars acquired through galactic cannibalism. Every time the Milky Way has assimilated a smaller galaxy, it has absorbed the galaxy's stellar population. These stars continue to exist, now orbiting within our galaxy's halo. They are the former inhabitants of destroyed civilizations, immigrants drawn into our galaxy by the irresistible force of gravity. The Sagittarius dwarf galaxy alone has contributed tens of millions of stars. The stellar stream encircling the Milky Way contains approximately 100 million stars. These represent direct additions to the Milky Way's stellar census, formerly citizens of Sagittarius, now counted among our own. A population of 400 billion stars implies 400 billion potential opportunities for planetary systems. While not every star hosts planets, a significant proportion does. Conservative estimates suggest that 60% of stars possess at least one planet, translating to a minimum of 240 billion planets. The question then arises, how many of these are habitable? How many orbit within the zone where liquid water can exist? Estimates vary considerably. Conservative projections suggest that 1% of planets are potentially habitable, equating to 2.4 billion habitable worlds within our galaxy alone, a figure that has doubled from previous estimates. Even if life is exceptionally rare, occurring on perhaps 1 in a million habitable planets, this still leaves 2,400 worlds potentially harboring life within the Milky Way, again, double the prior estimation. Furthermore, if intelligent life is even more scarce, found on 1 in a billion planets, we are still looking at 2 or 3 civilizations somewhere out there. The Drake equation, used to estimate the number of communicative extraterrestrial civilizations, now has every one of its variables significantly increased. More stars, more planets, more opportunities. The probability of discovering alien intelligence has consequently risen substantially. While not guaranteed, it is now considerably more likely. This leads to a rather unsettling question. If there are 400 billion stars, and we have only detailed knowledge of a fraction of them, what might be concealed within the vast datasets? What peculiar celestial objects might lurk in the outer reaches of the halo? Rogue planets, nascent stars, black holes, neutron stars, objects we haven't even conceived of yet. Every star possesses a unique narrative. Its genesis in a collapsing cloud of gas, its life sustained by hydrogen fusion, and its eventual demise as a white dwarf, neutron star, or black hole. 400 billion individual stories, 400 billion lifetimes unfolding simultaneously across the vast expanse of the galaxy. Our Sun is merely one among these 400 billion stars. It is an average, unremarkable entity, a single voice lost within a choir so immense that individual notes are rendered inaudible. We are not special. We are not unique. We are but one star system amongst hundreds of billions. And that number has just doubled. The galaxy has become twice as crowded. This stark reality makes our perceived cosmic solitude even more perplexing. With such an abundance of stars, planets, and consequently chances, where is everyone else? 400 billion stars. And yet, we have received no communication from any other civilization. The doubling of stars and planets inherently doubles the likelihood that we are not alone. The expanded scale of the Milky Way fundamentally reshapes the search for extraterrestrial life. We begin by considering habitable zones. Each star possesses a region where planets receive an optimal amount of heat to sustain liquid water. If a planet is too close, water evaporates. Too far, it freezes solid. This zone's location is contingent upon the star's size and temperature. Red dwarf stars have minuscule habitable zones situated very close to the star. Sun-like stars exhibit zones comparable to Earth's orbit. Giant stars possess habitable zones located further away. 400 billion stars translate to 400 billion potential habitable zones. While not all these zones will host planets, a substantial number are expected to. The Kepler Space Telescope's discoveries have confirmed that planets are ubiquitous, occurring with extraordinary frequency. Most stars are orbited by at least one planet, and many host multiple planetary systems. Planetary systems are the norm, not the exception. Applying a conservative estimate, if 60% of stars possess planets, this yields 240 billion planetary systems. Now, let's consider the fraction of these systems that include planets within their habitable zones. A plausible estimation might be 10%, resulting in 24 billion potentially habitable planets within our galaxy alone, a figure that has doubled from prior estimations. However, habitability does not automatically equate to habitation. A planet can possess liquid water yet remain sterile, lifeless, and barren. Life requires more than just water. It necessitates the correct chemical composition, appropriate energy sources, and suitable conditions sustained over billions of years. The rarity of life is a profound unknown. We have but one data point, Earth. All other conclusions are speculative. Some scientists hypothesize that life is an inevitable outcome given the right conditions. Others contend that it is extraordinarily rare, a cosmic fluke, a 1 in a trillion anomaly. Let us assume, for argument's sake, that life is moderately rare, emerging on 1 in 1,000 habitable planets. This still implies 24 million living worlds within the Milky Way, a doubling of previous estimates. 24 million planets where biological processes occur, where cells divide, where evolution operates, where organisms adapt and survive. It is probable that the majority of this life is rudimentary, consisting of bacteria, single-celled organisms, or simple life forms. Intelligence, on the other hand, is far rarer. Earth existed for 3 billion years, populated solely by microbes. The emergence of complex multicellular life occurred relatively recently in geological time. Intelligence appeared only yesterday on the cosmic timescale. If intelligence is found on 1 in a million living worlds, this suggests 24 intelligent species exist within the galaxy. The precise number remains uncertain, but doubling the galaxy's size has consequently doubled the probability. Regardless of the exact figure, it has now increased by a factor of 2. The Fermi paradox, which questions the apparent absence of extraterrestrial civilizations despite the high probability of their existence, becomes even more acute. If there are so many opportunities for life, so many potential civilizations, why have we not detected any signals? Why are there no alien probes or artifacts? Why does the galaxy appear so empty? Some theories propose the existence of a great filter, a barrier that prevents civilizations from achieving interstellar capability. This filter might lie in our past, meaning life is inherently difficult to initiate, and we were exceptionally fortunate. Alternatively, the filter could lie in our future, suggesting that civilizations tend to self-destruct through nuclear warfare, climate collapse, or uncontrolled artificial intelligence. It is possible that we are currently approaching this very filter. Other hypotheses posit that intelligence is even rarer than currently conceived, suggesting that we might be one of very few, or perhaps even alone in the Milky Way, with 400 billion stars and only one civilization, ourselves, isolated and solitary, the sole voices in a silent galaxy. However, there is a hopeful perspective to consider. Doubling the number of stars means doubling the chance of contact. If civilized indicators, such as specific atmospheric chemicals suggesting life, are present, the James Webb Space Telescope is already embarking on this endeavor. Each newly discovered habitable planet represents an additional opportunity to detect life. Twice the number of worlds implies a greater probability that we are not alone. The odds have shifted in favor of life. This is not certainty or definitive proof, but rather an improvement in probabilities. And enhanced probabilities bring hope. Somewhere within the Milky Way, orbiting one of its 400 billion stars, life may be observing us in return, contemplating the same profound questions, experiencing a similar sense of cosmic isolation, and harboring the same hope for connection. The galaxy has just expanded, the chances have improved, and the search continues with renewed vigor. Imagine standing at the very edge of the Milky Way and gazing outward. Where does the galaxy truly end, and the vastness of intergalactic space begin? The answer, intriguingly, is nowhere definitive. There is no abrupt boundary. Instead, there is a gradual dissolution into the encroaching darkness. This is a rather uncomfortable truth. Galaxies do not possess distinct borders. They gracefully fade, with stars thinning out progressively, dark matter density diminishing gradually, and gas dispersing into the cosmic void. At what precise juncture does a galactic entity cease to be classified as such? The query lacks a definitive, clean-cut resolution. Consider the Earth's atmospheric envelope. Its termination is not marked by an abrupt boundary. Instead, air pressure gradually diminishes with increasing altitude. At sea level, we experience 1 atmosphere of pressure. At an elevation of 10 miles, this pressure is almost negligible. By 100 meters, it is practically a vacuum. Yet, technically speaking, atmospheric particles extend thousands of miles upwards. So, where does the atmosphere definitively end? It's an arbitrary demarcation. Analogous to this, the Milky Way operates under similar definitional ambiguities. Star density is at its zenith at the galactic core, reaching approximately 1 million stars per cubic light-year. As we venture outward towards our solar vicinity, this density reduces to about 10 stars per cubic light-year. Moving further still, we find 1 star per 10 cubic light-years. At the extremities of the halo, there is but 1 star per 1,000 light-years. Continue this progression, and eventually, we reach densities of 1 star per million light-years, or per billion, or per trillion. These numbers progressively shrink towards zero, but never quite attain it. Somewhere in that vast expanse, solitary stars drift alone. These are rogue objects, possibly ejected from the galaxy, yet not entirely adrift in the void of intergalactic space. Do they still qualify as Milky Way stars? This hinges entirely on one's chosen definition. Dark matter presents a comparable conundrum. Its halo extends far beyond the visible stellar populations. Precisely how far? Current models suggest a reach of at least 250,000 light-years, potentially extending to 400,000, or even 600,000 light-years. Eventually, the density of dark matter dwindles to such an extent that it seamlessly melds with the cosmic background radiation. Dark matter is ubiquitous. Trace amounts exist even in the vast stretches of intergalactic space. The transition is fluid, continuous, and lacks a sharp boundary. Gaseous nebulae further obscure any clear delineation of galactic edges. The Milky Way generates powerful galactic winds. Supernova explosions expel material outwards. This ejected gas travels hundreds of thousands of light-years before it disperses. Is this expelled gas still considered part of the galaxy? It originated from within, and it is expected to eventually fall back. However, at this moment, it resides far beyond any reasonable definition of the galactic boundary. The Magellanic Stream serves as a perfect illustration of this conceptual difficulty. Gas stripped from the large and small Magellanic Clouds forms a celestial stream stretching across the sky, approximately 600,000 light-years in length. This gas is no longer a component of the Magellanic Clouds. It is not yet part of the Milky Way either. It exists in a state of limbo, a transitional space. Satellite galaxies introduce further complexity. They orbit the Milky Way, yet they are classified as distinct celestial bodies. The reason for this classification? They possess their own stellar populations and internal structures. However, they are gravitationally tethered to us. Ultimately, they are destined to merge with our galaxy. Are they considered part of the Milky Way or not? Both interpretations can be valid, depending on the specific context. The viral radius attempts to address this definitional challenge. It establishes a boundary wherein objects are gravitationally bound to the central galaxy. Within this radius, all celestial bodies move in coordinated orbits. Beyond it, objects tend to drift independently. For the Milky Way, this concept yields a figure of approximately 250,000 light-years, representing a seemingly precise and definitive boundary. However, this boundary is not as absolute as it appears. Objects situated beyond the viral radius can still experience the gravitational influence of the Milky Way. This influence, while weak, is sufficient to be measurable and impactful, even if not strong enough to dictate stable orbits. The gravitational field of the galaxy extends indefinitely, gradually weakening but never truly ceasing to exist. Light originating from the Milky Way travels eternally. These photons continue their journey, carrying information about our galaxy across the vastness of the cosmos. In this sense, the Milky Way's influence is effectively infinite. Every star that has ever ignited within our galaxy has emitted light in all directions. That light persists in its travel, marking our galactic presence across immense cosmic distances. What does this imply in practical terms? When we attempt to ascertain the size of the Milky Way, we are essentially making a choice. We are selecting a specific definition, deciding what to include and what to exclude. The measurement of 200,000 light-years, for instance, utilizes the viral radius. This is a reasonable and defensible criterion, but it does not represent an absolute, immutable truth. Another astronomer might opt for a different definitional framework, perhaps based on the point where star density falls below a certain threshold, or where dark matter density diminishes to a specific level, or where satellite galaxies cease their orbital motion around us. Each of these definitional approaches yields a different size estimate. None of these estimates are inherently incorrect, nor are any of them perfectly accurate. The galaxy does not possess a distinct edge, because the universe itself is a continuous entity. Matter is distributed smoothly throughout it. Density gradients slope gently, without sharp discontinuities. Boundaries are essentially human constructs, imposed upon a cosmos that remains indifferent to our attempts at categorization. We reside within a galaxy that gradually fades into the seemingly infinite void. It lacks discernible walls or definitive borders, offering no clear termination, only a gentle transition from concentrated matter to emptiness, from our immediate vicinity to the boundless unknown. Measuring the nuances of this transition proves to be a more formidable task than quantifying the galaxy itself. The Milky Way is, in essence, a cannibalistic entity. Our galaxy has expanded to its present dimensions by consuming others. Hundreds of smaller galaxies have been drawn into our gravitational embrace, torn apart, and absorbed. Their constituent stars have become integral parts of our own. This is how galaxies achieve growth, not through gradual accretion, but through acts of cosmic violence, galactic mergers, and outright cannibalism. Larger galaxies prey upon smaller ones. The strong, gravitationally dominant entities consume the weaker ones. It is a matter of survival for the gravitationally massive. Evidence of these ancient galactic meals surrounds us. Stellar streams, resembling ethereal ribbons, encircle the galaxy. Each stream represents the remnants of a dwarf galaxy that ventured too close. The Milky Way, in its gravitational might, ripped these smaller galaxies asunder, stretching their stars into elongated formations. These stellar streams persist in orbit for billions of years, before eventually dispersing entirely. The Sagittarius dwarf galaxy is currently undergoing this process of consumption. It is an active instance of galactic predation. We have observed this event in progress. The Sagittarius dwarf galaxy contains an estimated 400 million stars. Over the span of the next billion years, these stars will become dispersed throughout the Milky Way. In 2 billion years, there will be no discernible trace of the Sagittarius dwarf galaxy remaining, save for spectral echoes within the data. However, Sagittarius is merely the most recent victim. Our galaxy has engaged in numerous such absorptions throughout its history. The Gaian-Enceladus merger, occurring approximately 10 billion years ago, represents a significant event. A galaxy roughly 1/4 the mass of the Milky Way at that time collided with us. This was not a minor dwarf galaxy, it was a substantial entity. The collision was undeniably violent, inflicting damage on both galaxies, but the Milky Way ultimately prevailed. We assimilated Gaia Enceladus entirely. Its stellar population now populates our galactic halo, numbering in the billions. These are the former inhabitants of a destroyed civilization. The Gaia spacecraft identified this ancient merger by meticulously analyzing stellar motions. Stars originating from Gaia Enceladus exhibit orbital characteristics distinct from those of native Milky Way stars. They move in retrograde directions, possess tilted orbits, and follow eccentric paths. Their orbital dynamics betray their extragalactic origin. Chemical analysis further corroborates this finding. Stars from Gaia Enceladus possess different elemental compositions compared to native stars, generally containing fewer heavy elements and exhibiting distinct abundance patterns. They formed in a separate galaxy with a unique chemical evolutionary history. Now, they orbit within our galaxy, having been captured and assimilated. The Kraken merger predates this, occurring approximately 11 billion years ago. This was an even more massive cosmic collision. Kraken may have constituted as much as half the mass of the Milky Way at that time. This merger profoundly reshaped our galaxy, triggering intense bursts of star formation and contributing significantly to the structure of our current galactic disk. The remnants of Kraken are more challenging to pinpoint due to their thorough integration, but they are undeniably present, comprising billions of stars. Evidence of past cannibalism includes the Sequoia dwarf, the Helmy streams, Omega Centauri, a colossal globular cluster, and the Magellanic Clouds, all destined for assimilation. The Sagittarius dwarf is in the process of digestion. Smaller dwarf galaxies that orbit too closely are also doomed. In the future, the Andromeda Galaxy is slated to collide with us. This event will represent the ultimate cosmic feast, a merger that will completely transform our galaxy. Galactic cannibalism offers a compelling explanation for the continuous growth of massive galaxies. The principle of the rich becoming richer applies. Once a galaxy achieves a certain mass, its gravitational influence extends over a wider region. It can then capture more celestial victims, consume them, and thereby increase its own size. This augmented size, in turn, enhances its capacity to capture even more victims. This creates a positive feedback loop, leading to runaway growth. Dwarf galaxies face a perilous existence. They are essentially prey, perpetually threatened by their larger galactic neighbors. The majority eventually succumb to consumption. Only a select few manage to survive in isolation. The Milky Way has established dominance within the local group by absorbing all proximate galaxies. We have forged an empire through relentless consumption. However, here lies the peculiar aspect. Those devoured galaxies are not truly gone. Their stars continue to exist, to shine, and to orbit. They now orbit within our galaxy. The Milky Way is not a singular entity, but rather a collective, a vast empire constructed from the remnants of dozens of smaller galaxies. It is conceivable that you yourself are composed of elements forged within a star that once belonged to Gaia Enceladus. Heavy elements such as iron and carbon undergo cyclical processes within the galaxy, released through supernova remnants and stellar winds. Eventually, these elements coalesce into our solar system, forming Earth and subsequently you. You are, in part, an alien entity, comprised of material originating from conquered galaxies. We are all effectively immigrants, citizens of an empire that eradicated borders by absorbing its neighbors. The Milky Way achieved its immense size through conflict, through mergers, and through cannibalism. And we continue this process, still consuming, still expanding, still augmenting our collection of stars pilfered from others. Scientists generally harbor an aversion to being proven incorrect. This is not primarily due to ego, but rather because being wrong necessitates a complete overhaul of established understanding, requiring recalculations, the rewriting of research papers, and the acknowledgement of inherent uncertainties. The James Webb Space Telescope compelled precisely such an admission of uncertainty. Launched in December of 2021, the Webb Telescope is a $6 billion infrared observatory, possessing 100 times the power of the Hubble Space Telescope. Its primary mission was to observe the earliest galaxies, the first stars, and the formative stages of cosmic structure. Few anticipated that it would revolutionize our comprehension of the Milky Way, yet it undeniably did. The pivotal breakthroughs stemmed from unexpected observations. The Webb telescope's capability to penetrate dust surpasses that of any prior instrument. Its infrared light can traverse gas and debris that obstruct visible light. This newfound clarity enabled Webb to map regions of the Milky Way that had previously remained obscured. These included the galactic center, dense clouds of dust, and the far side of the galactic disk. What Webb discovered astonished the scientific community. It revealed a greater degree of structure, a larger number of stars, and a more intricate complexity than existing models had predicted. The outer reaches of the galaxy were not the desolate voids we had presumed. Instead, faint stars populated regions we had assumed to be empty, scattered and isolated, yet numbering in the billions. Webb also provided unprecedented detail in its observations of satellite galaxies. It resolved individual stars within distant dwarf galaxies, enabling the measurement of their ages, chemical compositions, and distances. Each of these measurements contributed to refining our model of the Milky Way's gravitational field, and each refinement effectively pushed the galactic boundary further outward. Crucial data emerged from the analysis of stellar streams. Webb tracked these streams to distances far exceeding those observed by previous surveys. It measured streams at immense distances from the galactic center, extending to 200,000 light-years, and even 250,000 light-years. The very existence of these streams contradicted the notion that the galaxy was as small as we had previously estimated. Their presence served as definitive proof that our prior size calculations were erroneous. However, the most significant impact arose from mass estimations. Webb observed the subtle bending of light from distant galaxies as it passed around the Milky Way. This phenomenon, known as gravitational lensing, is a direct manifestation of Einstein's theory of general relativity. By measuring the degree of light bending, scientists could deduce the mass of the intervening galaxy. Webb's precision in these measurements surpassed that of previous instruments by several orders of magnitude. The resulting estimate indicated a mass of 4 trillion solar masses, potentially even more, which was triple the previous accepted figure. The data was irrefutable. Multiple independent methodologies corroborated this finding. While astronomers could debate theoretical models and proposed hypotheses, they could not dispute the direct measurements derived from gravitational lensing. Scientific conferences became venues for intense debate. Some astronomers staunchly defended the older measurements, while others readily embraced the new data. Research papers emerged advocating for both perspectives. Gradually, and with a degree of reluctance, the scientific consensus began to shift. The Milky Way was, in fact, considerably larger than previously believed. The established textbooks were demonstrably incorrect. The Webb telescope continues to refine these measurements. Each new observation adds further detail. Some measurements suggest an even greater galactic size, while others indicate that our estimations of the dark matter halo may still be underestimated. The final calculated size continues to increase. However, Webb has also raised new questions. If the Milky Way is indeed this vast, then other galaxies must also be similarly immense. Webb subsequently turned its attention to Andromeda, Triangulum, and other distant galaxies, prompting a reassessment across virtually every subdiscipline of astronomy. This iterative process is fundamental to the scientific endeavor. New instruments reveal novel data. This data, in turn, challenges existing models. These models are subsequently updated or entirely replaced. While few relish the experience of being proven wrong, the alternative is to remain entrenched in error, clinging to outdated concepts simply because they offer a sense of comfort, refusing to acknowledge evidence because it presents an inconvenient truth. The Webb telescope provided the compelling evidence, necessitated the admission of error, and compelled scientists to confront the data, thereby acknowledging their past mistake. The Milky Way is not the galaxy we once thought we knew. It is larger, more massive, and more complex than we comprehended. We are still in the process of discovering its true, immense scale. The James Webb Space Telescope has fundamentally altered our perspective, not through grand discoveries of distant cosmic structures, but through meticulous observations of our own immediate cosmic neighborhood. In doing so, it has illuminated the profound extent of our prior lack of understanding about our home galaxy. Dark energy represents the most profound enigma in cosmology. It is an invisible force that propels the universe apart, accelerating its expansion and causing space itself to stretch. Scientists have identified its existence, quantified its effects, and assigned it a name, yet its fundamental nature remains elusive. The discovery of larger galaxies has only amplified this mystery. The issue arises because calculations pertaining to dark energy are contingent upon accurate mass estimations. It is imperative to ascertain the total amount of matter present, its distribution, and the strength of its gravitational pull. Subsequently, all gravitational attraction is subtracted from the observed cosmic expansion rate. The residual force is attributed to dark energy, the phenomenon driving the accelerated outward movement. However, if galaxies are, in fact, twice as massive as previously measured, they contain significantly more matter. Increased matter implies enhanced gravity. Greater gravitational influence would suggest that the universe should be expanding at a slower rate. Yet, the expansion rate has not demonstrably decreased. Independent measurements, utilizing distant supernovae, confirm this specific rate of cosmic acceleration. Therefore, if the matter content has doubled while the expansion rate remains constant, dark energy must either be more potent than initially calculated, distributed differently, or perhaps not uniformly present across space. The standard cosmological model posits that dark energy is a constant entity throughout the universe, possessing uniform strength and properties, a cosmological constant, considered a fundamental attribute of space. The existence of larger galaxies challenges this fundamental assumption. If more matter exerts an inward pull, a greater amount of dark energy would be required to generate the observed acceleration. This alters the ratio and shifts the balance. Dark energy might be more powerful than we currently believe, or our entire conceptualization of dark energy could be fundamentally flawed. Alternative theoretical frameworks exist, including modified gravity theories, variable dark energy density models, and considerations of cosmic inhomogeneities. Each of these theories attempts to explain the universe's behavior without assuming absolute uniformity. The existence of larger galaxies provides these alternative theories with greater scope for application. Consider the so-called coincidence problem. Dark energy and dark matter contribute roughly equivalent proportions to the universe's overall energy budget, with dark energy accounting for approximately 70%, dark matter for about 25%, and normal matter for a mere 5%. The question arises, why these specific ratios? Why not a 90-10 split or a 50-50 distribution? This perceived similarity appears suspect. Doubling the amount of dark matter by postulating larger galaxies exacerbates this coincidence. Under such circumstances, even more dark energy would be required to maintain the observed ratio, or one must concede that the ratio itself has changed. In either scenario, this coincidence demands a satisfactory explanation. Some cosmologists propose that this coincidence is not coincidental at all, suggesting that dark energy and dark matter might be interconnected, perhaps representing different manifestations of the same underlying phenomenon. If galaxies harbor greater quantities of dark matter, it is conceivable that they also generate or interact with more dark energy within their immediate vicinity. Testing this hypothesis presents significant challenges. Dark energy is invisible, appears uniform, and, as far as our measurements indicate, remains constant. It cannot be directly observed with telescopes, captured, or studied in isolation. Its effects can only be inferred through its influence on cosmic expansion. Larger galaxies also impact baryon acoustic oscillations, which manifest as ripples in the large-scale distribution of galaxies across the universe, essentially frozen sound waves from the early cosmos. Cosmologists utilize these oscillations as standard rulers, measuring the spacing between ripples to calculate distances. These distance measurements, in turn, are crucial for estimating the influence of dark energy. However, these ripples are intrinsically linked to galaxy clustering, the number of galaxies, their masses, and their spatial distribution. If galaxies are larger and more massive, the patterns of clustering change, the ripples shift, and the standard ruler becomes less reliable. Consequently, distance measurements require recalculation, leading to corresponding adjustments in dark energy estimates. The Hubble tension, a persistent disagreement between different methods of measuring the universe's expansion rate, is further exacerbated by these findings. Local measurements, employing supernovae, yield one set of figures, while observations of the cosmic microwave background radiation, which remarkably aligns with observations across 13 billion years of cosmic history, provide another. However, the cosmic microwave background model incorporates free parameters, specifically values for dark matter and dark energy, which we can measure but do not fully comprehend. If these measurements are inaccurate, the entire cosmological model becomes unstable. The existence of larger galaxies introduces significant instability into this foundational model, not to an extent that causes immediate collapse, but enough to instill a sense of unease among cosmologists. It raises questions about the certainty of our understanding of dark energy. The universe is undeniably accelerating its expansion. That is a confirmed fact. However, the underlying reasons for this acceleration and the precise contribution of dark energy to this process have become considerably more uncertain. Our miscalculation of galactic sizes implies a potential miscalculation of the universe's overall properties as well. Dark energy remains the most profound mystery in physics, and this mystery has just deepened considerably. 200,000 light-years. This is the current consensus figure. The Milky Way spans approximately 200,000 light-years in diameter, perhaps reaching 250,000. The precise number remains dependent on the definition employed for its edge. However, this is not the definitive answer. It represents the most accurate assessment available at this juncture. Within the next decade, this figure is likely to change. Advancements in telescope technology, improved data acquisition, and a deeper understanding will inevitably lead to refinements in measurement. This iterative process is constant. What we can state with a high degree of confidence is that the galaxy is considerably larger than the previously estimated 100,000 light-years. That older figure is definitively inaccurate. We possess compelling evidence from multiple, independent observational techniques. These include the study of stellar streams, analysis of satellite galaxies, mapping of dark matter distribution, and gravitational lensing observations. Every methodology consistently points towards a larger galactic extent. The figure of 200,000 light-years aligns well with current observational data. It is consistent with the orbital characteristics of satellite galaxies. It adequately explains the trajectories of stellar streams. It also corresponds with established dark matter models. This estimate is reasonable, defensible, and likely close to the actual size, but it is by no means final. What critical measurements are we still missing? Numerous. We require more comprehensive maps of the dark matter halo. Current models largely extrapolate from observations within the inner regions, assuming specific density profiles. Direct measurements of the outer halo remain scarce. Enhanced gravitational lensing surveys would provide invaluable data. The discovery of additional satellite galaxies would further refine our understanding of their orbits. Improved computational simulations are essential for testing theoretical predictions. We need deeper surveys targeting faint stars. The outer halo is populated by dim red dwarf stars scattered across vast expanses. Current telescopes can only detect the nearest of these stars. How many others remain hidden beyond our current detection limits? Are there entire populations of stars we are currently unaware of? Future telescopes, with their increased sensitivity, will probe deeper into these regions. Each incremental improvement in sensitivity will reveal more stars, and each new discovery will extend the perceived boundary of the galaxy outward. We require more precise distance measurements. The distances to many stellar streams are still uncertain. Are they located 150,000 light-years away or 200,000? This inherent uncertainty complicates the process of drawing definitive boundaries. Enhanced parallax measurements, particularly from the Gaia mission, will prove beneficial. However, for streams orbiting at extreme distances from the galactic center, parallax measurements become exceedingly difficult. We need to develop new observational techniques. Furthermore, our understanding of galactic winds requires improvement. Hot gas is expelled from the galactic disk. How far does this gas extend? At what point does it re-enter the galactic gravitational influence? Does this expelled gas still constitute a part of the galaxy? The dynamics of these winds significantly impact mass estimations and influence where we delineate the boundary between the galaxy and intergalactic space. We need to discover more satellite galaxies. While approximately 60 satellite galaxies are currently known for the Milky Way, simulations predict the existence of hundreds. Where are these missing satellites? Are they too faint to be detected with current technology? Do they orbit at such extreme distances that our observational surveys have not yet encompassed those regions? Each newly identified satellite galaxy provides crucial insights into the Milky Way's gravitational reach. We need to measure the Magellanic Clouds with greater precision. Are they permanently gravitationally bound to the Milky Way, or are they merely passing through on temporary orbits? Their orbital paths are directly influenced by the total mass of the Milky Way. Precise measurement of their orbits will allow for a refined estimation of the galaxy's mass, which in turn will impact the estimated galactic size. We need to clarify the point where our galaxy ceases and the Andromeda galaxy begins. It is possible that their respective dark matter halos are already in contact, but the precise location of this interface remains undetermined. How can we differentiate between two interpenetrating halos? This is not merely an academic question. It is crucial for determining the exact moment when the collision between the two galaxies will commence. The Nancy Grace Roman Space Telescope, scheduled for launch in the near future, is expected to play a significant role in addressing these questions. This telescope is designed to survey vast areas of the sky with unprecedented depth, enabling the detection of faint satellite galaxies, the mapping of distant stellar streams, and the measurement of gravitational lensing across extensive fields of view. Every collection of data will sharpen our perception of the Milky Way. The colossal telescope will also be instrumental. This terrestrial behemoth, boasting a mirror exceeding 100 feet in diameter, possesses a resulting capability unparalleled by any construction prior. It will focus on individual celestial bodies within neighboring galaxies. Their speeds will be accurately ascertained. Each data point further refines our understanding of the galaxy's mass and dimensions. Subsequent explorations will continuously augment the total figure. 200,000 light-years might evolve to 220,000, or 180,000, or 250,000. The range of potential values will diminish. Our certainty will ascend. However, the figure will never achieve absolute perfection, nor will it ever be definitive, merely progressively more accurate. This is the significance of all these efforts. We inhabit a galaxy whose dimensions we are still in the process of quantifying. Its scale is so vast that a complete observation is impossible. We are situated within it, striving to chart its expanse, cognizant that our perspective is inherently constrained, incomplete, and influenced by our position. 200,000 light-years represents our most accurate estimate at present. The future will bring improved tools, superior information, and more precise conclusions. The process of measurement persists. The galaxy continues to unveil its secrets. And we continue to grasp the immense scope of our dwelling place. The Milky Way is larger than we previously conceived, twice as broad, possessing 3 times the mass, containing 400 billion stars, an incalculable number of planets, and billions of potential abodes for life. And we have only just commenced to comprehend its true magnitude. This is the galaxy we call home. Immense, intricate, still enigmatic, perpetually expanding, and continuously teaching us that our knowledge is less comprehensive than we presume. The ultimate figure. We have not yet attained it. And it is possible we never will. Nevertheless, we are drawing nearer. With each observation, with each new finding, with each unveiled truth. The Milky Way spans 200,000 light-years in width.